What's going on? So today I'm reading through Toy Models of Superposition by Anthropic. This is a really important paper, one that I've heard a lot about, haven't read in full. I've skimmed through it. Looks like there's some good diagrams to go through. And yeah, I'm just going to read this whole thing start to finish and try to understand it as best as I can. Toy Models of Superposition. It would be very convenient if the individual neurons of artificial neural networks corresponded to cleanly interpretable features of the input. For example, in an ideal ImageNet classifier, each neuron would fire only in the presence of a specific visual feature, such as the color red, a left-facing curve, or a dog snout. Empirically, in models we have studied, some of the neurons do cleanly map to features, but it isn't always the case that features correspond so cleanly to neurons, especially in large language models, where it actually seems rare for neurons to correspond to clean features. This brings up many questions. Why is it that neurons sometimes align with features and sometimes don't? Why do some models and tasks have many of these clean neurons, while they're vanishingly rare in others? In this paper, we use toy models, small ReLU networks trained on synthetic data with sparse input features, to investigate how and when models represent more features than they have dimensions. We call this phenomenon superposition. When features are sparse, superposition allows compression beyond what a linear model would do at the cost of interference that requires nonlinear filtering. Consider a toy model where we train an embedding of 5 features of varying importance. In 2 dimensions, add a ReLU afterwards for filtering and vary the sparsity of the features. With dense features, the model learns to represent an orthogonal basis of the most important 2 features, similar to what principal component analysis might give us, and the other 3 features are not represented. But if we make the features sparse, this changes. So here we see a diagram. As sparsity increases, models use superposition to represent more features than dimensions. And the rightward pointing arrow represents increasing feature sparsity. At 0% sparsity, we see that the 2 most important features are given dedicated orthogonal dimensions, while other features are not embedded. So less important features map to 0, and we see 2 orthogonal lines going off in different directions in different quadrants. 80% sparsity. The 4 most important features are represented as antipodal pairs. The least important features are not embedded. So in this diagram, we just see 4 lines, or really 2 lines that form a cross. All of the lines are orthogonal to each other. 90% sparsity. All 5 features are embedded as a pentagon, but there is now positive interference. So here we see a pentagonal, conglomeration of 5 lines with slight interference representing that none of them are truly orthogonal. And the most important feature is in yellow here, and there's medium important features. There's about 2 or 3 medium, there's 1 medium important feature. Well, I don't know. It kind of goes to green. Long story short, there's really 1 most important feature, and there's 4 less important features. And, oh cool, you can reproduce this in a collab notebook. Cool. Not only can models store additional features in superposition by tolerating some interference, but we'll show that, at least in certain limited cases, models can perform computation while in superposition. In particular, we'll show that models can put simple circuits computing the absolute value function in superposition. This leads us to hypothesize that the neural networks we observe in practice are in some sense noisily simulating larger, highly sparse networks. In other words, it's possible that models we train can be thought of as doing the same thing as an imagined much larger model representing the exact same features but with no interference. Feature superposition isn't a novel idea. A number of previous interpretability papers have considered it, and it's very closely related to the long-studied topic of compressed sensing in mathematics, as well as the ideas of distributed, dense, and population codes in neuroscience and deep learning. What then is the contribution of this paper? For interpretability researchers, our main contribution is providing a direct demonstration that superposition occurs in artificial neural networks given a relatively natural setup, suggesting this may also occur in practice. That is, we show a case where interpreting neural networks as having sparse structure in superposition isn't just a useful post hoc interpretation, but actually the ground truth of a model. We offer a theory of when and why this occurs, revealing a phase diagram for superposition. This explains why neurons are sometimes monosemantic, responding to a single feature, and sometimes polysemantic, responding to many unrelated features. We also discover that, at least in our toy model, superposition exhibits complex geometric structure. But our results may also be of broader interest. We find preliminary evidence that superposition may be linked to adversarial examples and grokking, and might also suggest a theory for the performance of mixture of experts models. More broadly, the toy model we investigate has unexpectedly rich structure, exhibiting phase changes, a geometric structure based on uniform polytypes, or polytopes, energy level like jumps during training, and a phenomenon which is qualitatively similar to the fractional quantum Hall effect in physics, among other striking phenomena. We originally investigated the subject to gain understanding of cleanly interpretable neurons in larger models, but we found these toy models to be surprisingly interesting in their own right. Key results from our toy models. In our toy models, we are able to demonstrate that superposition is a real observed phenomenon. Both monosemantic and polysemantic neurons can form. At least some kinds of computation can be performed in superposition. Whether features are stored in superposition is governed by a phase change. Superposition organizes features into geometric structures such as digons, triangles, pentagons, and tetrahedrons. Our toy models are simple ReLU networks, so it seems fair to say that neural networks exhibit these properties in at least some regimes, but it's very unclear what to generalize to real networks. Definitions and motivation, features, directions, and superposition. In our work, we often think of neural networks as having features of the input represented as directions in activation space. This isn't a trivial claim. It isn't obvious what kind of structure we should expect neural network representations to have. When we say something like word embeddings have a gender direction, or vision models have curve detector neurons, one is implicitly making strong claims about the structure of network representations. Despite this, we believe this kind of linear representation hypothesis is supported both by significant empirical findings and theoretical arguments. One might think of this as two separate properties, which we'll explore in more detail shortly. Decomposability. Network representations can be described in terms of independently understandable features. Linearity. Features are represented by direction. Let's read that again to really let it sink in. We believe this kind of linear representation hypothesis is supported both by significant empirical findings and theoretical arguments. One might think of this as two separate properties, which we'll explore in more detail shortly. Decomposability. Network representations can be described in terms of independently understandable features. Linearity. Features are represented by direction. If we hope to reverse engineer neural networks, we need a property like decomposability. Decomposability is what allows us to reason about the model without fitting the whole thing in our heads. It's not enough for things to be decomposable. We need to be able to access the decomposition somehow. In order to do this, we need to identify the individual features within a representation. In a linear representation, this corresponds to determining which directions in activation space correspond to which independent features of the input. Sometimes, identifying feature directions is very easy because features seem to correspond to neurons. For example, many neurons in the early layers of Inception V1 clearly correspond to features, e.g. curve detector neurons. Why is it that we sometimes get this extremely helpful property, but in other cases don't? We hypothesize that there are really two countervailing forces driving this. Privilege basis. Only some representations have a privilege basis, which encourages features to align with basis directions, i.e. to correspond to neurons. Superposition. Linear representations can represent more features than dimensions, using a strategy we call superposition. This can be seen as neural networks simulating larger networks. This pushes features away from corresponding to neurons. Superposition has been hypothesized in previous work, and in some cases, assuming something like superposition has been shown to help find interpretable structure. However, we're not aware of feature superposition as having been unambiguously demonstrated to occur in neural networks before. One paper demonstrates a closely related phenomenon of model superposition. The goal of this paper is to change that, demonstrating superposition and exploring how it interacts with privileged bases. If superposition occurs in networks, it deeply influences what approaches to interpretability research make sense, so unambiguous demonstration seems important. The goal of this section will be to motivate these ideas and unpack them in detail. It's worth noting that many of the ideas in this section have close connections to ideas in other lines of interpretability research, especially disentanglement, neuroscience, distributed representations, population codes, etc., compressed sensing, and many other lines of work. This section will focus on articulating our perspective on the problem. We'll discuss these other lines of work in detail in related work. Empirical phenomena. When we talk about features and how they're represented, this is ultimately theory building around several observed empirical phenomena. Before describing how we conceptualize those results, we'll simply describe some of the major results motivating our thinking. Word embeddings. A famous result by Mikolov et al. Found that word embeddings appear to have directions which correspond to semantic properties, allowing for embedding arithmetic vectors such as v king equals v man plus v woman equals v queen. I might have misread that. Let me read it again. The vector for king minus the vector for man plus the vector for woman is equal to the vector for queen. Latent spaces. Latent spaces. Similar vector arithmetic and interpretable direction results have also been found for generative adversarial networks. Interpretable neurons. There is a significant body of results finding neurons which appear to be interpretable in RNNs, in CNNs, in GANs, activating in response to some understandable property. This work has faced some skepticism. In response, several papers have aimed to give extremely detailed accounts of a few specific neurons, in the hope of dispositively establishing examples of neurons which truly detect some understandable property, notably Camarada et al., but also two other papers. Universality. Many analogous neurons responding to the same properties can be found across networks. Polysemantic neurons. At the same time, there are also many neurons which appear to not respond to an interpretable property of the input, and in particular, many polysemantic neurons which appear to respond to unrelated mixtures of inputs. As a result, we tend to think of neural network representations as being composed of features which are represented as directions. We'll unpack this idea in the following sections. What are features? Our use of the term feature is motivated by the interpretable properties of the input we observe neurons or word embedding directions responding to. There's a rich variety of such observed properties. We'd like to use the term feature to encompass all these properties, but even with that motivation, it turns out to be quite challenging to create a satisfactory definition of a feature. Rather than offer a single definition we're confident about, we consider three potential working definitions. Features as arbitrary functions. One approach would be to define features as any function of the input, but this doesn't quite seem to fit our motivations. There's something special about these features that we're observing. They seem to, in some sense, be fundamental abstractions for reasoning about the data, with the same features forming reliably across models. Features also seem identifiable. Cat and car are two features, while cat plus car and cat minus car seem like mixtures of features rather than features in some important sense. Features as interpretable properties. All the features we described are strikingly understandable to humans. One could try to use this for a definition. Features are the presence of human understandable concepts in the input, but it seems important to allow for features we might not understand. If AlphaFold discovers some important chemical structure for predicting protein folding, it very well might not be something we initially understand. Neurons in sufficiently large models. A final approach is to define features as properties of the input which a sufficiently large neural network will reliably dedicate a neuron to representing. For example, curve detectors appear to reliably occur across sufficiently sophisticated vision models, and so are a feature. For interpretable properties which we presently only observe in polysemantic neurons, the hope is that a sufficiently large model would dedicate a neuron to them. This definition is slightly circular, but avoids the issues with the earlier ones. We've written this paper with the final neurons in sufficiently large models definition in mind, but we aren't overly attached to it, and actually think it's probably important to not prematurely attach to a definition. Features as directions. As we've mentioned in previous sections, we generally think of features as being represented by directions. For example, in word embeddings, gender and royalty appear to correspond to directions, allowing arithmetic like the vector for king minus the vector for man plus the vector for woman equals the vector for queen. Examples of interpretable neurons are also cases of features as directions, since the amount a neuron activates corresponds to a basis direction in the representation. Let's call a neural network representation linear if it Features correspond to directions in activation space. In a linear representation, each feature, f sub I, has a corresponding representation direction, weight matrix sub I. The presence of multiple features, or let's not assume anything, we'll just call it, has a corresponding representation direction, w sub I. The presence of multiple features, f1, f2, and so on, activating with values x of f1, x of f2, and so on, is represented by x sub f1 times big W sub f1 plus x sub f2 times big W f2, and so on. To be clear, the features being represented are almost certainly nonlinear functions of the input. It's only the map from features to activation vectors which is linear. Note that whether something is a linear representation depends on what you consider to be the features. We don't think it's a coincidence that neural networks empirically seem to have linear representations. Neural networks are built from linear functions interspersed with nonlinearities. In some sense, the linear functions are the vast majority of the computation, for example, as measured in flops. Linear representations are the natural format for neural networks to represent information in. Concretely, there are three major benefits. Linear representations are the natural outputs of obvious algorithms a layer might implement. If one sets up a neuron to pattern match a particular weight template, it will fire more as a stimulus matches the template better and less as it matches it less well. Linear representations make features linearly accessible. A typical neural network layer is a linear function followed by a nonlinearity. If a feature in the previous layer is represented linearly, a neuron in the next layer can select it and have it consistently excite or inhibit that neuron. If a feature were represented non-linearly, the model would not be able to do this in a single step. Statistical efficiency. Representing features as different directions may allow non-local generalization in models with linear transformations, such as the weights of neural nets. Increasingly, their statistical efficiency relative to models which can only locally generalize. This view is especially advocated in some of Bengio's writing. A more accessible argument can be found in this blog post. It is possible to construct nonlinear representations and retrieve information from them if you use multiple layers, although even these examples can be seen as linear representations with more exotic features. We provide an example in the appendix. However, our intuition is that nonlinear representations are generally inefficient for neural networks. One might think that a linear representation can only store as many features as it has dimensions, but it turns out this isn't the case. We'll see that the phenomenon we call superposition will allow models to store more features, potentially many more features, in linear representations. For discussion on how this view of features squares with the conception of features as being multidimensional manifolds, see the appendix, What About Multidimensional Features? Privileged versus non-privileged bases. Even if features are encoded as directions, a natural question to ask is what directions? In some cases, it seems useful to consider the basis directions, but in others it doesn't. Why is this? When researchers study word embeddings, it doesn't make sense to analyze basis directions. There would be no reason to expect a basis dimension to be different from any other possible direction. One way to see this is to imagine applying some random linear transformation m to the word embedding, and apply m inverse to the following weights. This would produce an identical model where the basis dimensions are totally different. This is what we mean by a non-privileged basis. Of course, it's possible to study activations without a privileged basis. You just need to identify interesting directions to study somehow, such as creating a gender direction in a word embedding by taking the difference vector between man and woman. But many neural network layers are not like this. Often, something about the architecture makes the basis direction special, such as applying an activation function. This breaks the symmetry, making those directions special, and potentially encouraging features to align with the basis dimensions. We call this a privileged basis, and call the basis directions neurons. Often, these neurons correspond to interpretable features. So here we see two diagrams. On the left, in a non-privileged basis, features can be embedded in any direction. There is no reason to expect basis dimensions to be special. Examples, word embeddings, transformer residual streams. And we see two lines, two arrows that seem to be orthogonal to each other, but they are making diagonal lines with the origin, with the two axes. In a privileged basis, there is an incentive for features to align with basis dimensions. This doesn't necessarily mean they will. Examples: convnet neurons, transformer MLPs. And in the diagram, we see two lines that are orthogonal to each other, and they're directly on each vertical and horizontal axis respectively. From this perspective, it only makes sense to ask if a neuron is interpretable when it is in a privileged basis. In fact, we typically reserve the word neuron for basis directions which are in a privileged basis. Note that having a privileged basis doesn't guarantee that features will be basis aligned. We'll see that they often aren't, but it's a minimal condition for the question to even make sense. The superposition hypothesis. Even when there is a privileged basis, it's often the case that neurons are polysemantic, responding to several unrelated features. One explanation for this is the superposition hypothesis. Roughly, the idea of superposition is that neural networks want to represent more features than they have neurons, so they exploit a property of high-dimensional spaces to simulate a model with many more neurons. Diagrams again. On the left, polysemanticity is what we'd expect to observe if features were not aligned with a neuron, despite incentives to align with the privileged basis. And here we see in the diagram the same two non-privileged basis vectors from before at an angle, or maybe it's not the same, but the idea is these two vectors going off that connect to each other orthogonally but are not privileged or on a privileged basis, and there's arrows bringing them in to the y-axis. And then on the left, we see in the superposition hypothesis, features can't align with the basis because the model embeds more features than there are neurons. Polysemanticity is inevitable if this happens. So here in the diagram, we see three vectors going off from the origin, and none of them are pulled toward the axis lines. And just to read this again, in the superposition hypothesis, features can't align with the basis because the model embeds more features than there are neurons. Polysemanticity is inevitable if this happens. Okay, and just to clarify, those three vectors going off from the origin are none of them are orthogonal to each other. Several results from mathematics suggest that something like this might be plausible. Almost orthogonal vectors. Although it's only possible to have n orthogonal vectors in an n-dimensional space, it's possible to have e to the n many almost orthogonal with less than epsilon cosine similarity vectors in high-dimensional spaces. See the Johnson-Linden-Strauss lemma. Interesting. Compressed sensing. In general, if one projects a vector into a lower dimensional space, one can't reconstruct the original vector. However, this changes if one knows that the original vector is sparse. In this case, it is often possible to recover the original vector. Concretely, in the superposition hypothesis, features are represented as almost orthogonal directions in the vector space of neuron outputs. Since the features are only almost orthogonal, one feature activating looks like other features slightly activating. Tolerating this noise or interference comes at a cost, but for neural networks with highly sparse features, this cost may be outweighed by the benefit of being able to represent more features. Crucially, sparsity greatly reduces the costs since sparse features are rarely active to interfere with each other, and nonlinear activation functions create opportunities to filter out small amounts of noise. So I'm going to reread this just to let it really sink in. Concretely, in the superposition hypothesis, features are represented as almost orthogonal directions in the vector space of neuron outputs. Since the features are only almost orthogonal, one feature activating looks like other features slightly activating. Tolerating this noise or interference comes at a cost, but for neural networks with highly sparse features, this cost may be outweighed by the benefit of being able to represent more features. Crucially, sparsity greatly reduces the costs since sparse features are rarely active to interfere with each other, and nonlinear activation functions create opportunities to filter out small amounts of noise. And here we see two diagrams. On the left, even if only one sparse feature is active, using linear dot product projection on the superposition leads to interference, which the model must tolerate or filter. So here we see one of the sparse features is active of 4 vectors going out from the origin. 5 vectors going out from the origin, and they're almost orthogonal from each other. And reading it again, even if only one sparse feature is active, using linear dot product projection on the superposition leads to interference, which the model must learn to tolerate. Yeah, and there's some interference lines coming off and making orthogonal lines with 2 of the other feature lines, I believe. Yes. And then on the right, if the features aren't as sparse as the superposition is expecting, multiple present features can additively interfere such that there are multiple possible nonlinear reconstructions of an activation vector. So here we see a similar image where that same line is firing, but unfortunately there's 2 other vectors which are firing greatly, so there's strong interference. Whereas in the last one, there was 1 line that was firing and 2 lines that were firing just a slight bit. So the interference was tolerable in that image. But in this new image, if the features aren't as sparse as the superposition is expecting, multiple present features can additively interfere such that there are multiple possible nonlinear reconstructions of an activation vector. Cool. One way to think of this is that a small neural network may be able to noisily simulate a sparse larger model. And here we have another diagram. Hypothetical disentangled model. Under the superposition hypothesis, the neural networks we observe are simulations of larger networks, in which every neuron is a disentangled feature. And then below this, we have a smaller model. These idealized neurons are projected onto the actual network as almost orthogonal vectors over the neurons. And in our observed model, which is significantly smaller, the network we observe is a low-dimensional projection of the larger network. From the perspective of individual neurons, this presents as polysemanticity. Although we've described superposition with respect to neurons, it can also occur in representations with an unprivileged basis, such as word embedding. Superposition simply means that there are more features than dimensions. Summary: a hierarchy of feature properties. The ideas in this section might be thought of in terms of 4 progressively more strict properties that neural network representations might have. Decomposability. Neural network activations which are decomposable can be decomposed into features, the meaning of which is not dependent on the value of other features. This property is ultimately the most important. See the role of decomposition in defeating the curse of dimensionality. Linearity. Features correspond to directions. Each feature, f sub I, has a corresponding representation direction, w sub I. The presence of multiple features, f1, f2, so on, activating with values x sub f1, x sub f2, and so on, is represented by x sub f1 times w sub f1 plus x sub f2 times w sub f2, and so on. Superposition versus non-superposition. A linear representation exhibits superposition if w transpose times w is not invertible. If w transpose times w is invertible, it does not exhibit superposition. Basis aligned. A representation is basis aligned if all w sub I are one-hot basis vectors. A representation is partially basis aligned if all w sub I are sparse. This requires a privileged basis. The first 2, decomposability and linearity, are properties we hypothesize to be widespread, while the latter, non-superposition and basis aligned, are properties we believe only sometimes occur. Demonstrating superposition. If one takes the superposition hypothesis seriously, a natural first question is whether neural networks can actually noisily represent more features than they have neurons. If they can't, the superposition hypothesis may be comfortably dismissed. The intuition from linear models would be that this isn't possible. The best a linear model can do is to store the principal components. But we'll see that adding just a slight nonlinearity can make models behave in a radically different way. This will be our first demonstration of superposition. It will also be an object lesson in the complexity of even very simple neural networks. Experiment setup. Our goal is to explore whether a neural network can project a high-dimensional vector, x in Rn, into a lower dimensional vector, h within Rm, and then recover it. Here we see a diagram, hypothetical disentangled model. Our first experiments will test the extent to which the idealized activations of an imagined larger model can be stored and recovered from a lower dimensional space. So we see x within Rn, and that's going to the observed model via W, and in W we see h within Rm, which is going to the hypothetical disentangled model via W transpose. The feature vector, x. We begin by describing the high-dimensional vector x, the activations of our idealized, disentangled, larger model. We call each element x sub I a feature because we're imagining features to be perfectly aligned with neurons in the hypothetical larger model. In a vision model, this might be a Gabor filter, a curve detector, or a floppy ear detector. In a language model, it might correspond to a token referring to a specific famous person, or clause being a particular kind of description. Since we don't have any ground truth for features, we need to create synthetic data for x, which simulates any important properties we believe features have from the perspective of modeling them. We make three major assumptions. Feature sparsity. In the natural world, many features seem to be sparse in the sense that they only rarely occur. For example, in vision, most positions in an image don't contain a horizontal edge, or a curve, or a dog head. In language, most tokens don't refer to Martin Luther King, or aren't part of a clause describing music. This idea goes back to classical work on vision and the statistics of natural images. See, e.g., Olhausen, 1997, the section Why Sparseness. For this reason, we will choose a sparse distribution for our features. More features than neurons. There are an enormous number of potentially useful features a model might represent. This imbalance between features and neurons in real models seems like it must be a central tension in neural network representations. Features vary in importance. Not all features are equally useful to a given task. Some can reduce the loss more than others. For an ImageNet model, where classifying different species of dogs is a central task, a floppy ear detector might be one of the most important features it can have. In contrast, another feature might only very slightly improve performance. Concretely, our synthetic data is defined as follows. The input vectors x are synthetic data intended to simulate the properties we believe the true underlying features of our task have. We consider each dimension x sub I to be a feature. Each one has an associated sparsity, s sub I, and importance, I sub I. We let x sub I equal 0 with probability s sub I, but is otherwise uniformly distributed between 0 to 1. Interesting, so just to note, the sparsity of our feature represents the probability with which that feature equals 0. So if s sub I is huge, is 100%, then our feature is definitely going to be 0 because the sparsity is 100%. That makes sense. And if the sparsity is very low, then our feature will be very high, close to 1. So let's continue. We let x sub I equal 0 with probability s sub I, but is otherwise uniformly distributed between 0 to 1. In practice, we focus on the case where all features have the same sparsity, s sub I equals s. The model, x maps to x prime. We will actually consider two models, which we motivate below. The first linear model is a well-understood baseline which does not exhibit superposition. The second ReLU output model is a very simple model which does exhibit superposition. The two models vary only in the final activation function. So in our linear model we have h equals w times x. X prime equals w transpose times h plus b. X prime equals w transpose times w times x plus b. In our ReLU output model, h equals w times x. X prime equals ReLU of W transpose times H plus B, X prime equals the ReLU of X prime equals the ReLU of W transpose times W times X plus B. Why these models? The superposition hypothesis suggests that each feature in the higher dimensional model corresponds to a direction in the lower dimensional space. This means we can represent the down projection as a linear map, H equals Wx. Note that each column W sub I corresponds to the direction in the lower dimensional space that represents a feature X sub I. To recover the original vector, we'll use the transpose of the same matrix W transpose. This has the advantage of avoiding any ambiguity regarding what direction in the lower dimensional space really corresponds to a feature. It also seems relatively mathematically principled and empirically works. We also add a bias. One motivation for this is that it allows the model to set features it doesn't represent to their expected value. But we'll see later that the ability to set a negative bias is important for superposition for a second set of reasons. Roughly, it allows models to discard small amounts of noise. The final step is whether to add an activation function. This turns out to be critical to whether superposition occurs. In a real neural network, when features are actually used by the model to do computation, there will be an activation function, so it seems principled to include one at the end. The loss. Our loss is weighted mean squared error weighted by the feature importances I sub I described above. So L equals the sum for all x of the sum for all I of the importances for I times x sub I minus x prime sub I squared. Basic results. Our first experiment will simply be to train a few ReLU output models with different sparsity levels and visualize the results. We'll also train a linear model. If optimized well enough, the linear model solution does not depend on sparsity level. The main question is how to visualize the results. The simplest way is to visualize W transpose times W, a features by features matrix, and B, a feature length vector. Note that features are arranged from most important to least, so the results have a fairly nice structure. Here's an example of what this type of visualization might look like for a small model, model n equals 20, m equals 5, which behaves in the expected linear model-like way, only representing as many features as it has dimensions. So here we see a heat map for W transpose times W. It tends to be easier to visualize WTW than W. Here we see that WTW is an identity matrix for the most important features and 0 for less important ones. We can also look at the bias B. The bias is 0 for features learned to pass through. The bias is 0 for features learned to pass though, and the expected value, a positive number, for others. Weight slash bias element values, -1 on the right with blue and 1 on the left. I got those directions mixed. The idea should be plain in red. But the thing we really care about is this hypothesized phenomenon of superposition. Does the model represent extra features by storing them non-orthogonally? Is there a way to get at it more explicitly? Well, one question is just how many features the model learns to represent. For any feature, whether or not it is represented is determined by the norm of Wi, the norm of its embedding vector. We'd also like to understand whether a given feature shares its dimension with other features. For this, we calculate the sum sub j, the sum for all j not equal to I of W hat sub I dot W sub j squared, projecting all other features onto the direction vector of W sub I. It will be 0 if the feature is orthogonal to other features, dark blue below. On the other hand, values greater than or equal to 1 mean that there is some group of other features which can activate Wi as strongly as feature I itself. We can visualize the model we looked at previously this way. So here we see, we want to understand which features the model chooses to represent in its hidden representation and whether they are orthogonal to each other. And just to describe the image, you see the norm of Wi and a line with 5 black bars going down which represent features, in contrast to the above diagram with WTW and 5 red central squares on the diagonal, which all meant a bias of 1, or a weight of 1, my fault. And down below again, we want to understand which features the model chooses to represent in its hidden representation, and whether they're orthogonal to each other. To do this, we visualize the norm of each feature's direction vector, norm of Wi. This will be approximately 1 if a feature is fully represented, and 0 if it is not. For each feature, we also use color to visualize whether it is orthogonal to other features, i.e. in superposition. This model simply dedicates one dimension to each of the most important features, representing them orthogonally. And which makes sense because we see on the right a line of colors, a gradient showing that 0 is black, and all of these are black. And the superposition formula, the sum for all j, x hat sub I times x sub j squared. Now that we have a way to visualize models, we can start to actually do experiments. We'll start by considering models with only a few features: n equals 20, m equals 5, intensity, which I believe is what the I represents, but I just want to, importance, okay. So n equals 20, m equals 5, importance of I, or importance sub I equals 0.7 to the ith power. This will make it easy to visually see what happens. We consider a linear model and several ReLU output models trained on data with different feature sparsities. Here we have another diagram. On the left, you see linear model with WTW making that diagonal, and the norm for W sub I is just 5 orthogonal features. Linear models learn the top m features. 1 minus s equals 0.001 is shown. So very high sparsity, right? Yeah, 1 minus s being that low means s is very high, but others are similar. And then on the right of the dividing line, we see ReLU output models. So starting with 1 minus s equals 1, so the sparsity is very, very low. The sparsity is 0. WTW, same as in the linear model. Stepping up, so in the dense regime, ReLU output models also learn the top m features. Right, makes sense. Then when 1 minus s equals 0.3, so the sparsity is 70%. WTW, we see it continuing to move down the diagonal, but we see some blues coming off of the diagonal, which means negative weights or very low weights. And in the WI's norm plot, we see 3 orthogonal features, but then 4 more, which get increasingly light, which move increasingly toward 1 in that superposition equation. As sparsity increases, superposition allows models to represent more features. The most important features are initially untouched. This early superposition is organized in antipodal pairs. More on this later. And moving on, when 1 minus s equals 0.1, so the sparsity is at 90%. WTW, maybe I shouldn't say percent there, but you get the point. S is 0.9. WTW, and we see it's activating more. There are more lines coming off of the main diagonal where the weights are 1. I should be more specific. Those blue squares are activated. Those blue squares have a low weight, a negative weight value. However, they're coming off of the diagonal, which has a red value. And then below WI norm, there's one feature with no superposition, and many features. Well, to be specific, there's 2, 4, 6, 8 features with superposition. And again, as sparsity increases, superposition allows models to represent more features. The most important features are initially untouched. This early superposition is organized in antipodal pairs. And you continue to move up, you see more activation, you see everything is now superpositional once 1 minus s equals 0.03. Or at least every feature which does exist is superpositional, and the features go up as sparsity goes up and approaches 0. All the way on the right, you see 1 minus s equals 0.001, which means sparsity is at 0.999. WTW is a very populated matrix, and the norm WI is is representing many superpositional features. In the high sparsity regime, models put all features in superposition and continue packing more. Note that at this point we begin to see positive interference and negative biases. We'll talk about this more later. As our standard intuitions would expect, the linear model always learns the top m most important features, analogous to learning the top principal components. The ReLU output model behaves the same on dense features, 1 minus s equals 1. But as sparsity increases, we see superposition emerge. The model represents more features by having them not be orthogonal to each other. It starts with less important features, and gradually affects the most important ones. Initially, this involves arranging them in antipodal pairs, where one feature's representation vector is exactly the negative of the others, but we observe it gradually transition to other geometric structures as it represents more features. We'll discuss feature geometry further in the later section, the geometry of superposition. The results are qualitatively similar for models with more features and hidden dimensions. For example, if we consider a model with m equals 20 hidden dimensions and n equals 80 features, with importance increased to I sub I equals 0.9 to the ith power, to account for having more features, we observe essentially a rescaled version of the visualization above. So on the left, we see a linear model, 1 minus s equals 0.001, or any. It's a linear model, so the weights WTW are just always going to be orthogonal. Makes sense. On the right, we're zooming out. We're starting at 1 minus s equals 1.0 with a ReLU output model. It's still all orthogonal, but as we continue to increase the s, and s is the sparsity, we see that the model enters superposition for every feature. Makes sense. Mathematical understanding. In the previous section, we observed a surprising empirical result. Adding a ReLU to the output of our model allowed a radically different solution, superposition, which doesn't occur in linear models. The model where it occurs is still quite mathematically simple. Can we analytically understand why superposition is occurring? And for that matter, why does adding a single nonlinearity make things so different from the linear model case? It turns out that we can get a fairly satisfying answer, revealing that our model is governed by balancing two competing forces, feature benefit and interference, which will be useful intuition going forwards. We'll also discuss a connection to the famous Thomas problem in chemistry. Let's start with the linear case. This is well understood by prior work. If one wants to understand why linear models don't exhibit superposition, the easy answer is to observe that linear models essentially perform principal component analysis. But this isn't fully satisfying. If we set aside all our knowledge and intuition about linear functions for a moment, why exactly is it that superposition can't occur? A deeper understanding can come from the results of Sachs et al., who study the learning dynamics of linear neural networks, that is, neural networks without activation functions. Such models are ultimately linear functions, but because they are the composition of multiple linear functions, the dynamics are potentially quite complex. The punchline of their paper reveals that neural network weights can be thought of as optimizing a simple closed-form solution. We can tweak their problem to be a bit more simple to our linear case, revealing the following equation. L is from a probability distribution of the sum for all I of the importance for I times 1 minus the norm weights sub I squared all squared except for the importance, which is multiplied to it after, and again the sum for all I. Feature benefit is the value a model attains from representing a feature. In a real neural network, this would be analogous to the potential of a feature to improve predictions it represented accurately, plus the interference, the sum for all I not equal to j of importance of j, w sub j times w sub I squared. Interference between x sub I and x sub j occurs when two features are embedded non-orthogonally and, as a result, affect each other's predictions. This prevents superposition in linear models. The Sachs results reveal that there are fundamentally two competing forces which control learning dynamics in the considered model. Firstly, the model can attain a better loss by representing more features. We've labeled this feature benefit, but it also gets a worse loss if it represents more than it can fit orthogonally due to interference between features. In fact, this makes it never worthwhile for the linear model to represent more features than it has dimensions. Can we achieve a similar kind of understanding for the ReLU output model? Concretely, we'd like to understand L equals the integral of x, or of the norm squared of the importance times x minus the ReLU of WTW times x plus b. And that's, sorry, I'm just a little bit confused by the formatting here. I believe that's all times d, p of x, where x is distributed such that x sub I equals 0 with probability s. Okay? And again, that's just considering the sparsity. The integral over x decomposes into a term for each sparsity pattern according to the binomial expansion of 1 minus s plus s to the power of n. We can group terms of the sparsity together, rewriting the loss as L equals 1 minus s to the power of n times loss sub n plus all the way up to 1 minus s times s sub n minus 1 times L1 plus s to the n times L naught, with each L sub k corresponding to the loss when the input is a k-sparse vector. Note that as s maps to 1, L sub 1 and L sub 0 dominate. I think that's approaching. So note that as the sparsity approaches 1, L sub 1 and L naught dominate. The L sub 0 term, corresponding to the loss on a 0 vector, is just a penalty on positive biases. The sum for all I of the ReLU of bias I squared. So the interesting term is L sub 1, the loss on 1 sparse vectors. L sub 1 equals the sum for all I, the integral from 0 to 1. So 0 is less than or equal to x sub I, which is less than or equal to 1, of the importance of I times the square of x sub I minus ReLU of the squared norm of w sub I times x sub I plus b sub I. And then that sum is plus the sum for all I not equal to j of the integral from 0 to 1 of x sub I of the importance j times the ReLU of, or I should say the squared ReLU of w sub j times w sub I times x sub I plus b sub j. If we focus on the case x sub I equals 1, we get something which looks even more analogous to the linear case. The sum for all I of the importance I times 1 minus the ReLU of the squared norm of w sub I plus b sub I, and everything I said just then except the importance is squared. Feature benefit is similar to before. Note that ReLU never makes things worse, and that the bias can help when the model doesn't represent a feature by taking on the expected value. And so that sum plus the sum for all I not equal to j of the importance sub j times the squared ReLU of w sub j times w sub I plus b sub j. Interference is similar to before, but ReLU means that negative interference, or interference where a negative bias pushes it below zero, is free in the one sparse case. This new equation is vaguely similar to the famous Thomson problem in chemistry. In particular, if we assume uniform importance and that there are a fixed number of features with norm of W sub I equals 1, and the rest have the norm of W sub I equals 0, and that bias I equals 0, then the feature benefit term is constant, and the interference term becomes a generalized Thomson problem. We're just packing points on the surface of the sphere with a slightly unusual energy function. We'll see this can be a productive analogy when we resume our empirical investigation in the following sections. Another interesting property is that ReLU makes negative interference free in the one sparse case. This explains why the solutions we've seen prefer to only have negative interference when possible. Further, using a negative bias can convert small positive interferences into essentially being negative interferences. What about the terms corresponding to less sparse vectors? We leave explicitly writing these out to the reader, but the main idea is that there are multiple compounding interferences, and the active features can experience interference. In a later section, we'll see that features often organize themselves into sparse interference graphs, such that only a small number of features interfere with another feature. It's interesting to note that this reduces the probability of compounding interferences and makes the one sparse loss term more important relative to others. Superposition as a phase change. The results in the previous section seem to suggest that there are three outcomes for a feature when we train a model. 1. The feature may simply not be learned. 2. The feature may be learned and represented in superposition. Or 3. The model may represent a feature with a dedicated dimension. The transitions between these three outcomes seem sharp. Possibly, there's some kind of a phase change. One way to understand this better is to explore if there's something like a phase diagram from physics, which could help us understand when a feature is expected to be in one of these regimes. Although we can see hints of this in our previous experiment, it's hard to really isolate what's going on because many features are changing at once, and there may be interaction effects. As a result, we set up the following experiment to better isolate the effects. As an initial experiment, we consider models with two features but only one hidden layer dimension. We still consider the ReLU output model, ReLU of WTW times x minus b. The first feature has an importance of 1.0. On one axis, we vary the importance of the second feature. On one axis, we vary the importance of the second extra feature from 0.1 to 10. On the other axis, we vary the sparsity of all features from 1.0 to 0.01. We then plot the second extra feature is not learned. We then plot whether the second extra feature is not learned in superposition, or learned and represented orthogonally. To reduce noise, we train 10 models for each point and average over the results, discarding the model with the highest loss. We can compare this to a theoretical toy model of the toy model, where we can get closed form solutions for the loss of different weight configurations as a function of importance and sparsity. There are three natural ways to store two features in one dimension. W equals 1, 0, ignore 0, 1, throwing away the extra feature. W equals 0, 1, ignore 1, 0, throwing away the first feature to give the extra feature a dedicated dimension. And W equals 1, minus 1. Store the features in superposition, losing the ability to represent 1, 1, the combination of both features at the same time. We call this last solution antipodal because the two basis vectors 1, 0 and 0, 1 are mapped in opposite directions. It turns out we can analytically determine the loss for these solutions. And here we see a diagram, sparsity relative importance phase diagram, n equals 2, m equals 1. What happens to an extra feature if the model can't give each feature a dimension? There are three possibilities, depending on feature sparsity and the extra feature's importance relative to other features. Gray is extra feature not represented, blue is extra feature gets dedicated dimension, red is extra feature is stored in superposition. We can both study this empirically and build a theoretical model. So in the empirical version, the y is feature density and the x is the relative feature importance. Each configuration is colored by the norm and superposition of the extra feature. The sum sub j for x hat sub I times x sub j squared. And so in this empirical version, as the sparsity approaches 1, you get only not represented and dedicated dimensions. As the sparsity approaches 0, everything's in superposition. And below that, we see in the theoretical prediction, feature density. So I should note, in the empirical version, there's some fog or blur occurring, even as sparsity is very close to 1. But in the theoretical prediction, everything is very straight and cut off and well defined. There's no blur or fog. And again, the y-axis here is the feature density, 1 minus s, and the x-axis is the relative feature importance. So what we see not represented, extra feature is 0. We see w equals 1, 0, and w transpose is 0, 1. So it forms a diagonal matrix. Dedicated dimension, other not represented. So w equals 0, 1, w transpose is 1, 0. And superposition, antipodal pair. W equals 1 minus 1, W transpose 1, 1. As expected, sparsity is necessary for superposition to occur, but we can see that it interacts in an interesting way with relative feature importance. But most interestingly, there appears to be a real phase change observed in both the empirical and theoretical diagrams. The optimal weight configuration discontinuously changes in magnitude and superposition. In the theoretical model, we can analytically confirm that there's a first-order phase change. There's a crossover between the functions, causing a discontinuity in the derivative of the optimal loss. We can ask this same question of embedding 3 features in 2 dimensions. This problem still has a single extra feature, now the third one. We can study asking what happens as we vary its importance relative to the other 2 and change sparsity. For a theoretical model, we now consider 4 natural solutions. We can describe solutions by asking, what feature direction did W ignore? For example, W might just not represent the extra feature. We'll write this W is orthogonal to 0, 0, 1, or W might ignore one of the other features, W is orthogonal to 1, 0, 0. But the interesting thing is that there are 2 ways to use superposition to make antipodal pairs. We can put the extra feature in an antipodal pair with one of the others, W is orthogonal to 0, 1, 1. Or put the other 2 features in superposition and give the extra feature a dedicated dimension, W orthogonal to 1, 1, 0. Details on the closed form losses for these solutions can be found in this notebook. We do not consider a last solution of putting all the features in joint superposition, W orthogonal to 1, 1, 1. Sparsity relative importance phase diagram, N equals 3, M equals 2. Empirical version, we see for relevant feature importance, anything above 1.0x, we see the feature density 1 minus s, 0.01 to 1, and each configuration is colored by the norm and superposition of the extra feature. The sum sub j of the square of x hat sub I times x sub j. Theoretical prediction. And it looks similar, again, just no blur, everything is very straight. Relative feature importance on the x-axis and feature density on the y-axis. Not represented, W equals the matrix 1, 0, 0 in the top row and 0, 1, 0 on the bottom row, and W orthogonal to 0, 0, 1. Dedicated dimension, other not represented, W equals 0, 1, 0, 0, 0, 1. W is orthogonal to 1, 0, 0. Superposition, W equals 1, 0, 0, 0, 1, negative 1, and W orthogonal to 0, 1, 1. Dedicated dimension, others in superposition, W equals 1, negative 1, 0, 0, 0, 1. W orthogonal to 1, 1, 0. These diagrams suggest that there really is a phase change between different strategies for encoding features. However, we'll see in the next section that there is much more complex structure this preliminary view doesn't capture. The geometry of superposition. We've seen that superposition can allow a model to represent extra features, and that the number of extra features increases as we increase sparsity. In this section, we'll investigate this relationship in more detail, discovering an unexpected geometric story. Features seem to organize themselves into geometric structures such as pentagons and tetrahedrons. In some ways, the structure described in this section seems too elegant to be true, and we think there's a good chance it's at least partly idiosyncratic to the toy model we're investigating. But it seems worth investigating because if anything about this generalizes to real models, it may give us a lot of leverage in understanding their representations. We'll start by investigating uniform superposition, where all features are identical, independent, equally important, and equally sparse. It turns out that uniform superposition has a surprising connection to the geometry of uniform polytopes. Later, we'll move on to investigate non-uniform superposition, where features are not identical. It turns out that this can be understood, at least to some extent, as a deformation of uniform superposition. Uniform superposition. As mentioned above, we begin our investigation with uniform superposition, where all features have the same importance and sparsity. We'll see later that this case has some unexpected structure, but there's also a much more basic reason to study it. It's much easier to reason about than the non-uniform case, and has fewer variables we need to worry about in our experiments. We'd like to understand what happens as we change feature sparsity, S. Since all features are equally important, we will assume without loss of generality that each feature has importance, I sub I equals 1. We'll study a model with n equals 400 features and m equals 30 hidden dimensions, but it turns out the number of features and hidden dimensions doesn't matter very much. In particular, it turns out that the number of input features n doesn't matter as long as it's much larger than the number of hidden dimensions, n greater than m. And it also turns out that the number of hidden dimensions doesn't really matter as long as we're interested in the ratio of features learned to hidden features. Doubling the number of hidden dimensions just doubles the number of features the model learns. A convenient way to measure the number of features the model has learned is to look at the Frobenius norm. So the squared Frobenius norm, or I should just say the squared norm of W sub f. I'm not sure how to pronounce the symbol for Frobenius norm. I guess you just say Frobenius norm, but I'm trying to read off all the math. Since the Frobenius norm of W is approximately 1 if a feature is represented and approximately 0 if it is not, this is roughly the number of features the model has learned to represent. Conveniently, this norm is basis independent, so it still behaves nicely in the dense regime S equals 0, where the feature basis isn't privileged by anything and the model represents features with arbitrary directions instead. We'll plot d star equals m over the Frobenius norm of W, which we can think of as the dimensions per feature, and see in this line plot number of hidden dimensions per embedded feature. Unexpectedly, we find that the number of dimensions per feature is sticky at 1 and 1/2. We denote this with a straight dotted line. So you see at 1, it's roughly straight. It continues to decrease as the model becomes more sparse. And around 1/2, it also becomes straight again, and then continues to decrease. Surprisingly, we find that this graph is sticky at 1 and 1/2. This very vaguely resembles the fractional quantum Hall effect. Why is this? On inspection, the 1/2 sticky point seems to correspond to a precise geometric arrangement where features come in antipodal pairs, each being exactly the negative of the other, allowing two features to be packed into each dimension, each hidden dimension. It appears that antipodal pairs are so effective that the model preferentially uses them over a wide range of the sparsity regime. It turns out that the antipodal pairs are just the tip of the iceberg. Hiding underneath this curve are a number of extremely specific geometric configurations of features. Feature dimensionality. In the previous section, we saw that there is a sticky regime where the model has half a dimension per feature in some sense. This is an average statistical property of the features the model represents, but it seems to hint at something interesting. Is there a way we could understand what fraction of a dimension a specific feature gets? We'll define the dimensionality of the ith feature, d sub I, as d sub I equals the norm squared w sub I over the sum for all j, w hat I times w sub j squared, where w sub I is the weight vector column associated with the ith feature, and w hat sub I is the unit version of that vector. Intuitively, the numerator represents the extent to which a given feature is represented, while the denominator is how many features share the dimension it is embedded in, by projecting each feature onto its dimension. In the antipodal case, each feature participating in an antipodal pair will have a dimensionality of d equals 1 over 1 plus 1 equals 1 half, while features which are not learned will have a dimensionality of 0. Empirically, it seems that the dimensionality of all features add up to the number of embedding dimensions when the features are packed efficiently in some sense. We can now break the above plot down on a per feature basis. This reveals many more of these sticky points. To help us understand this better, we're going to create a scatter plot annotated with some additional information. We start with the line plot we had in the previous section. We overlay this with a scatter plot of the individual feature dimensionalities for each feature in the models at each sparsity level. The feature dimensionalities cluster at certain fractions, so we draw lines for these. It turns out that each fraction corresponds to a specific weight geometry. We'll discuss this shortly. We visualize the weight geometries for a few models with a feature geometry graph, where each feature is a node and edge weights are based on the absolute value of the dot product feature embedding vectors, so features are connected if they aren't orthogonal. Let's look at the resulting plot, and then we'll try to figure out what it's showing us. So feature geometry, each node corresponds to a feature. Edge weights are the absolute value of the dot product of feature embeddings. Features are colored if they are embedded as one of the geometric structures listed below. So you see in this same descending plot, which stalls at 1/2, the dedicated dimension is just a dot. The tetrahedron, 3/4, 4 features in 3 dimensions. The triangle, and this is as the sparsity increases, features are embedded or tend to be embedded as these geometric structures. Model learns non-basis aligned features without sparsity. Nothing makes the basis dimension special. And the amount of these features not learned, or at least these non-basis aligned features, continue to decrease as sparsity increases, and eventually this is on the log scale, so 1 over 1 minus s, and eventually as it reaches 3 or 2.5, really, these non-basis aligned features disappear. Nothing makes the basis dimension special. And again, to talk about the geometry, at what point? Roughly, I guess 3/4, or here it's, 3/4 you get the tetrahedron with 4 features in 3 dimensions. At 2/3 you get the triangle, 3 features in 2 dimensions. Then the diagon, antipodal pair, 2 features in 1 dimension. The pentagon, 5 features in 2 dimensions. And then the square antiprism, 8 features in 3 dimensions. What is going on with the points clustering at specific fractions? We'll see shortly that the model likes to create specific weight geometries and kind of jumps between the different configurations. In the previous section, we developed a theory of superposition as a phase change, but everything on this plot between 0, not learning a feature, and 1, dedicating a dimension to a feature, is superposition. Superposition is what happens when features have fractional dimensionality. That is to say, superposition isn't just one thing. How can we relate this to our original understanding of the phase change? We often think of water as only having 3 phases: ice, water, and steam. But this is a simplification. There are actually many phases of ice, often corresponding to different crystal structures, e.g. hexagonal versus cubic ice. In a vaguely similar way, neural network features seem to also have many other phases within the general category of superposition. Why these geometric structures? In the previous diagram, we found that there are distinct lines corresponding to dimensionality of 3/4 tetrahedron, 2/3 triangle, 1 over 2 antipodal pair, 2 over 5 pentagon, 3 over 8 square prism, and 0 feature not learned. We believe that there would also be a 1 dedicated dimension for a feature line, if not for the fact that basis features are indistinguishable from other directions in the dense regime. Several of these configurations may jump out as solutions to the famous Thomson problem. In particular, square antiprisms are much less famous than cubes and are primarily of note for their role in molecular geometry due to being a Thomson problem solution. As we saw earlier, there is a very real sense in which our model can be understood as solving a generalized version of the Thomson problem. When our model chooses to represent a feature, the feature is embedded as a point on an m-dimensional sphere. A second clue as to what's going on is that there are lines for the Thomson solutions which are uniform polyhedra, e.g. tetrahedron, but there seem to be split lines where we'd expect to see non-uniform solutions, e.g. instead of a 3 over 5 line for triangular bipyramids, we see a co-occurrence of points at 2 over 3 for triangles and points at 1 over 2 for antipodes. In a uniform polyhedron, all vertices have the same geometry, and so if we embed features as them, each feature has the same dimensionality. But if we embed features as a non-uniform polyhedron, different features will have more or less interference with others. In particular, many of the Thomson solutions can be understood as Tegum products, an operation which constructs polytopes by embedding two polytopes in orthogonal subspaces of smaller uniform polytopes. In the earlier graph visualizations of feature geometry, two subgraphs are disconnected if and only if they are in different Tegum factors. As a result, we should expect their dimensionality to actually correspond to the underlying factor uniform polytopes. Here we see three diagrams. A triangular bipyramid is the Tegum product of a triangle and an antipode. As a result, we observe 3 times 2 over 3 features and 2 times 1.5 features, rather than 3 times 3 over 5 features. To the right of that, we see a pentagonal bipyramid is the Tegum product of a pentagon and an antipode. As a result, we observe 2 times 2 over 5 features and 2 times 1 over 2 features, rather than 7 times 3 over 7 features. An octahedron is the Tegum product of 3 antipodes. This doesn't change the observed lines, since 3 over 6 equals 1/2. This also suggests a possible reason why we observe 3D Thomson problem solutions, despite the fact that we're actually studying a higher dimensional version of the problem. Just as many 3D Thomson solutions are Tegum products of 2D and 1D solutions, perhaps higher dimensional solutions are often Tegum products of 1D, 2D, and 3D solutions. The orthogonality of factors in Tegum products has interesting implications. For the purposes of superposition, it means that there can't be any interference across Tegum factors. This may be preferred by the toy model. Having many features interfere simultaneously could be really bad for it. Aside, polytopes and low-rank matrices. At this point, it's worth making explicit that there's a correspondence between polytopes and symmetric, positive definite, low-rank matrices, i.e. matrices of the form WTW. This correspondence underlies the results we saw in the previous section and is generally useful for thinking about superposition. In some ways, the correspondence is trivial. If one has a rank M n by n matrix of the form, if one has a rank m n by n matrix of the form WTW, then W is a n by m matrix. We can interpret the columns of W as n points in a m-dimensional space. The place where this starts to become interesting is that it makes it clear that WTW is driven by geometry. In particular, we can see how the off-diagonal terms are driven by the geometry of the points. Put another way, there is an exact correspondence between polytopes and strategies for superposition. For example, every strategy for putting 3 features in superposition in a 2-dimensional space corresponds to a triangle, and every triangle corresponds to such a strategy. From this perspective, it doesn't seem surprising that if we have 3 equally important and equally sparse features, the optimal strategy is an equilateral triangle. So in this diagram, we see triangle equals m equals 3 columns of W, forming the lines, the vectors that go off to these 3 points. WTW as graph on W. These points form a triangle of vertices or of edges. WTW as matrix, it has a 1 on the diagonal and negative 1/2 at every other point. And orthogonal vectors, W orthogonal to 1, 1, 1. Down a row, we see square, m equals 4, decomposes into two digons, these straight vectors with points at each end. WTW as graph on W creates what would you call it? It's interesting here because they have the lines connecting as a cross rather than a square, which actually makes complete sense. Actually doesn't make complete sense. To me, at least. I'm sure it makes complete sense mathematically and rigorously. At least I hope it does. But next to that, we see WTW as matrix. A 1 on the diagonal, and for example, a 1, 0, negative 1 in both the first column and first row, and that pattern continues. And then orthogonal vectors, W orthogonal to 1, 0, 1, 0, W orthogonal to 0, 1, 0, 1. This correspondence also goes the other direction. Suppose we have a rank n minus I matrix of the form WTW. We can characterize it by the dimensions W did not represent, that is, which directions are orthogonal to W. For example, if we have a n minus 1 matrix, we might ask what single direction did W not represent. This is especially informative if we assume that WTW will be as identity-like as possible, given the constraint of not representing certain vectors. In fact, given such a set of orthogonal vectors, we can construct a polytope by starting with n basis vectors and projecting them to a space orthogonal to the given vectors. For example, if we start in 3 dimensions and then project such that W is orthogonal to 1, 1, 1, we get a triangle. More generally, setting W orthogonal to 1, 1, 1, and so on gives us a regular n simplex. This is interesting because it's in some sense the minimal possible superposition. Assuming that features are equally important and sparse, the best possible direction to not represent is the fully dense vector of 1s. Non-uniform superposition. So far, this section has focused on the geometry of uniform superposition, where all features are of equal importance, equal sparsity, and independent. The model is essentially solving a variant of the Thompson problem. Because all the features are the same, solutions corresponding to uniform polyhedra get especially low loss. In this subsection, we'll study non-uniform superposition, where features are somehow not uniform. They may vary in importance and sparsity, or have a correlational structure that makes them non-independent. This distorts the uniform geometry we saw earlier. In practice, it seems like superposition in real neural networks will be non-uniform, so developing an understanding of it seems important. Unfortunately, we're far from a comprehensive theory of the geometry of non-uniform superposition at this point. As a result, the goal of this section will merely be to highlight some of the more striking phenomena we observe. Features varying in importance or sparsity causes smooth deformation of polytopes as the imbalance builds, up until a critical breaking point at which they snap to another polytope. Correlated features prefer to be orthogonal, often forming in different Tegum factors. As a result, correlated features may form an orthogonal local basis. When they can't be orthogonal, they prefer to be side by side. In some cases, correlated features merge into a single feature. This hints at some kind of interaction between superposition-like behavior and PCA-like behavior. Anti-correlated features prefer to be in the same Tegum factor when superposition is necessary. They prefer to have negative interference, ideally being antipodal. We attempt to illustrate these phenomena with some representative experiments below. Perturbing a single feature. The simplest kind of non-uniform superposition is to vary one feature and leave the others uniform. As an experiment, let's consider an experiment where we represent n equals 5 features in m equals 2 dimensions. In the uniform case, with importance I equals 1 and activation density 1 minus s equals 0.05, we get a regular pentagon. But if we vary one point, in this case we'll make it more or less sparse. We see the pentagram stretch to account for the new value. If we make it denser, activating more frequently, yellow, the other features repel from it, giving it more space. On the other hand, if we make it sparser, activating less frequently, blue, it takes less space and other points push toward it. If we make it sufficiently sparse, there's a phase change, and it collapses from a pentagon to a pair of digons with the sparser point at 0. The phase change corresponds to loss curves corresponding to the two different geometries crossing over it. This observation allows us to directly confirm that it is genuinely a first-order phase change. To visualize the solutions, we canonicalize them, rotating them to align with each other in a consistent manner. So here we see in a diagram, to study non-uniform sparsity, we consider models with 5 features, varying the sparsity of a single feature and observing how the resulting solutions change. We observe a mixture of continuous deformation and sharp phase changes. So on the left, diagonal square solutions, point we vary sparsity of in the middle, and then points going off, forming antipodal pairs and a sphere around them. When the sparsity of the varied point falls below a certain critical threshold, approximately 2.5 times less than others, the pentagon solution changes to 2 diagons. Note how vertices shift as sparsity changes. So the point we vary the sparsity of is out there. It's making this pentagon with on the origin with these other points, which are rotated. Parameters n equals 5, m equals 2, importance I equals 1, 1 minus s equals 0.05 baseline, relative feature density 1 over s. For this plot below, the pentagon-diagon phase change corresponds to a loss curve crossover. Gradient descent has trouble moving between solutions associated with different geometries. As a result, fitting the model will often produce non-optimal solutions. By characterizing and plotting these, we can see that each geometry creates a different loss curve, and that the pentagon-diagon phase change corresponds to a crossover between the curves. So we're in a diagon regime, then a pentagon regime. It starts diagon squares, very dimension dropped. As it goes on, we get pentagon regime. See the pentagonal line has a lower loss. The diagonal squares has a higher loss as they diverge, and then it reaches this plateau point and then continues to steadily decrease again. And then above it we see triangles, which have a higher loss, 6e to the negative 3. So these results seem to suggest, I'm not sure if I read the paragraph above. Gradient descent has trouble moving between solutions associated with different geometries. As a result, fitting the model will often produce non-optimal solutions. By characterizing and plotting these, we can see that each geometry creates a different loss curve, and that the pentagon-diagon phase change corresponds to a crossover between the curves. These results seem to suggest that, at least in some cases, non-uniform superposition can be understood as a deformation of uniform superposition, and jumping between uniform superposition configurations rather than a totally different regime. Since uniform superposition has a lot of understandable structure, but real-world superposition is almost certainly non-uniform, this seems very promising. The reason pentagonal solutions are not on the unit circle is because models reduce the effect of positive interference, setting a slight negative bias to cut off noise and setting their weights to the norm of w sub I equals 1 over 1 minus b sub I to compensate. Distance from the unit circle can be interpreted as primarily driven by the amount of positive interference. A note for reimplementations. Optimizing with a 2-dimensional hidden space makes this easier to study, but the actual optimization process to be really challenging from gradient descent, a lot harder than even just having 3 dimensions. Getting clean results required fitting each model multiple times and taking the solution with the lowest loss. However, there's a silver lining to this. Visualizing the suboptimal solutions on a scatter plot as above allows us to see the loss curves for different geometries and gain greater insight into the phase change. Correlated and anticorrelated features. A more complicated form of non-uniform superposition occurs when there are correlations between features. This seems essential for understanding superposition in the real world, where many features are correlated or anticorrelated. For example, one very pragmatic question to ask is whether we should expect polysemantic neurons to group the same features together across models. If the groupings were random, you could use this to detect polysemantic neurons by comparing across models. However, we'll see that correlational structure strongly influences which features are grouped together in superposition. The behavior seems to be quite nuanced, with a kind of order of preferences for how correlated features behave in superposition. The model ideally represents correlated features orthogonally, in separate Tegum factors with no interactions between them. When that fails, it prefers to arrange them so that they're as close together as possible. It prefers positive interference between correlated features over negative interference. Finally, when there isn't enough space to represent all the correlated features, it will collapse them and represent their principal component instead. Conversely, when features are anti-correlated, models prefer to have them interfere, especially with negative interference. We'll demonstrate this with a few experiments below. Set up for exploring correlated and anti-correlated features. Throughout this section, we'll refer to correlated feature sets and anti-correlated feature sets. Correlated feature sets. Our correlated feature sets can be thought of as bundles of co-occurring features. One can imagine a highly idealized version of what might happen in an image classifier. There could be a bundle of features used to identify animals, fur, ears, eyes, and another bundle used to identify buildings, corners, windows, doors. Features from one of these bundles are likely to appear together. Mathematically, we represent this by linking the choice of whether all the features in a correlated feature set are zero or not together. Recall that we originally defined our synthetic distribution to have features be zero with probability S and otherwise uniformly distributed between 0 and 1. We simply have the same sample determine whether they're zero. Anti-correlated feature sets. One could also imagine anti-correlated features, which are extremely unlikely to occur together. To simulate these, we'll have anti-correlated feature sets where only one feature in the set can be active at a time. To simulate this, we'll have the feature set be entirely zero with probability S, but then only have one randomly selected feature in the set be uniformly sampled from 0 to 1, if it's active with the others being 0. Organization of correlated and anti-correlated features. For our initial investigation, we simply train a number of small toy models with correlated and anti-correlated features and observe what happens. To make this easy to study, we limit ourselves to the m=2 case, where we can explicitly visualize the weights as points in 2D space. In general, such solutions can be understood as a collection of points on a unit circle. To make solutions easy to compare, we rotate and flip solutions to align with each other. Models prefer to represent correlated features in orthogonal dimensions. We train several models with two sets of two correlated features, n=4 total, and a m=2 hidden dimensions. We then visualize the weight column for each feature. For ease of comparison, we rotate and flip solutions to have a consistent orientation. So blue and red denote correlated feature sets. Correlated feature sets are constructed by having them always co-occur, i.e. be zero or not at the same time. Models prefer to represent anti-correlated features in opposite directions. We train several models with two sets of two anti-correlated features, n=4 total, and a m=2 hidden dimensions. We then visualize the weight column for each feature. For ease of comparison, we rotate and flip solutions to have a consistent orientation. And blue and red denote anti-correlated feature sets. Anti-correlated feature sets are constructed by having them never co-occur, i.e. be zero or not at the same time. Models prefer to arrange correlated features side by side if they can't be orthogonal. We train several models with three sets of two correlated features, n=6, and a m=2 hidden dimensions. We then visualize the weight column for each feature. For ease of comparison, we rotate and flip solutions to have a consistent orientation. Note that models will not embed 6 independent features as a hexagon like this. So blue, red, and green denote correlated feature sets. Sometimes correlated feature sets collapse. In this case, it's an optimization failure, but we'll return to it shortly as an important phenomenon. Local almost orthogonal bases. It turns out that the tendency of models to arrange correlated features to be orthogonal is actually a quite strong phenomenon. In particular, for larger models, it seems to generate a kind of local almost orthogonal basis, where, even though the model as a whole is in superposition, the correlated feature sets considered in isolation are nearly orthogonal and can be understood as having very little superposition. To investigate this, we train a larger model with two sets of correlated features and visualize WTW. Here we see WTW with a heat map. Models prefer to represent correlated features in orthogonal dimensions, creating local orthogonal bases. We train a model with two sets of 10 correlated features, n equals 20 total, with m equals 10 hidden dimensions. Within each set of correlated features, the model creates a local orthogonal basis, having each feature be represented orthogonally. And the weight element values are 1 on the diagonal, and then you see the upper right and lower left quadrant have these collections of some positive and a greater proportion of negative weight values, and then the upper left and lower right quadrants, other than the diagonal, have 0 for their weights. If this result holds in real neural networks, it suggests we might be able to make a kind of local non-superposition assumption, where for certain sub-distributions, we can assume that the activating features are not in superposition. This could be a powerful result, allowing us to confidently use methods such as principal component analysis, which might not be principal to use generally in the context of superposition. Collapsing of correlated features. One of the most interesting properties is that there seems to be a trade-off with principal component analysis and superposition. If there are two correlated features A and B, but the model only has capacity to represent one, the model will represent their principal component, A plus B over the square root of 2, a sparse variable that has more impact on the loss than either individually, and ignore the second principal component, A minus B over square root of 2. As an experiment, we consider 6 features organized into 3 sets of correlated pairs. Features in each correlated pair are represented by a given color, red, green, and blue. The correlation is created by having both features always activate together. They're either both 0 or neither 0. The exact non-zero values they take when they activate is uncorrelated. As we vary the sparsity of the features, we find that in the very sparse regime, we observe superposition as expected, with features arranged in a hexagon and correlated features side by side. As we decrease sparsity, the features progressively collapse into their principal components. In very dense regimes, the solution becomes equivalent to PCA. So the solution is more like PCA, very dense. Most PCA-like solution, approximately 0.5, less than or equal to 1 minus S. Solutions involve more superposition as we move to the right, and eventually, all sets of features collapse, 2 sets of features collapse, 1 set of features collapse, and then no features collapse. Correlated feature set, approximately 1 minus S, less than or equal to 0.05. These results seem to hint that principal component analysis and superposition are in some sense complementary strategies which trade off with one another. As features become more correlated, principal component analysis becomes a better strategy. As features become sparser, superposition becomes a better strategy. When features are both sparse and correlated, mixtures of strategies seem to occur. It would be nice to more deeply understand this space of trade-offs. It's also interesting to think about this in the context of continuous equivariant features, such as features which occur in different rotations. Superposition and learning dynamics. The focus of this paper is how superposition contributes to the functioning of fully trained neural networks, but as a brief detour, it's interesting to ask how our toy models and the resulting superposition evolve over the course of training. There are several reasons why these models seem like a particularly interesting case for studying learning dynamics. Firstly, unlike most neural networks, the fully trained models converge to a simple but non-trivial structure that rhymes with an emerging thread of evidence that neural network learning dynamics might have geometric weight structure that we can understand. One might hope that understanding the final structure would make it easier for us to understand the evolution over training. Secondly, superposition hints at surprisingly discrete structure, regular polytopes of all things. We'll find that the underlying learning dynamics are also surprisingly discrete, continuing an emerging trend of evidence that neural network learning might be less continuous than it seems. Finally, since superposition has significant implications for interpretability, it would be nice to understand how it emerges over training. Should we expect models to use superposition early on, or is it something that only emerges later in training, as models struggle to fit more features in? Unfortunately, we aren't able to give these questions the detailed investigation they deserve within the scope of this paper. Instead, we'll limit ourselves to a couple particularly striking phenomena we've noticed, leaving more detailed investigation for future work. Phenomenon 1. Discrete energy level jumps. Perhaps the most striking phenomenon we've noticed is that the learning dynamics of toy models with large numbers of features appear to be dominated by energy level jumps, where features jump between different feature dimensionalities. Recall that a feature's dimensionality is the fraction of a dimension dedicated to representing a feature. Let's consider the problem setup we studied when investigating the geometry of uniform superposition in the previous section, where we have a large number of features of equal importance and sparsity. As we saw previously, the features ultimately arrange themselves into a small number of polytopes with fractional dimensionalities. A natural question to ask is what happens to these feature dimensionalities over the course of training. Let's pick one model where all the features converge into digons and observe. In the first plot, each colored line corresponds to the dimensionality of a single feature. The second plot shows how the loss curve changes over the same duration. So in this diagram, the feature dimensionality, we see it starts out a bunch of strands that eventually converge, some to 1/2, the others to 0. And that these oddities and convergence, it's hard to describe without looking at the plot. But if you're looking at the plot, you see how these phase changes correspond to different levels in the loss curve. So originally, the loss eventually starts to go down as these lines become threads on 0 and 0.5. And then some of these, which are at 0, go up to 0.5. And the loss stops from being at a plateau and descends again before plateauing again. Note how the dimensionality of some features jump between different values and swap places. As this happens, the loss curve also undergoes a sudden drop, a very small one at the first jump and a larger one at the second jump. These results make us suspect that seemingly smooth decreases of the loss curve in larger models are in fact composed of many small jumps of features between different configurations. For similar results of sudden mechanistic changes, see Olson et al.'s induction head phase change and Nanda and Lieberum's results on phase changes in modular arithmetic. More broadly, consider the phenomenon of grokking. Phenomenon 2. Learning as geometric transformations. Many of our toy model solutions can be understood as corresponding to geometric structures. This is especially easy to see and study when there are only m=3 hidden dimensions. Since we can just directly visualize the feature embeddings as points in 3D space forming a polyhedron, it turns out that, at least in some cases, the learning dynamics leading to these structures can be understood as a sequence of simple, independent geometric transformations. One particularly interesting example of this phenomenon occurs in the context of correlated features, as studied in the previous section. Consider the problem of representing n=6 features in superposition within m=3 dimensions. If we have the 6 features be two sets of 3 correlated features, we observe a really interesting pattern. The learning proceeds in distinct regimes, which are visible in the loss curve, with each regime corresponding to a distinct geometric transformation. So here we have a diagram: feature, weight, trajectories, top in 3D perspective. Blue and green denote correlated feature sets. Note that the resulting triangular antiprism is equivalent to a octahedron, with features forming antipodal pairs with features from a different correlated feature set. So initially, weights are initialized randomly close to 0. Then the first change in training is that the two sets of correlated features push apart one axis. Then next, each set of correlated features expands into a triangle. Finally, the triangles rotate into an antiprism. And at each set of these changes, the loss curve somewhat dips. I should say that if we look at the training steps, at 10 to the 2, it's still at the first initial randomized close to 0 weights. And so it continues to go down, and we see it steps down and then reaches B, and then it's plateauing for a little bit, then it steps down and reaches C, and it plateaus for a bit, then it goes down again and reaches D. The loss curve goes through several distinct regimes corresponding to different geometric transformations of the weights as seen above. Although the last solution An octahedron with features from different correlated sets arranged in antipodal pairs seems to be a strong attractor. The learning trajectory visualized above appears to be one of a few different learning trajectories that attract the model. The different trajectories vary at step C. Sometimes the model gets pulled directly into the antiprism configuration from the start, or organized features into antipodal pairs. Presumably, this depends on which feature geometry the model is closest to when step B ends. The learning dynamics we observe here seem directly related to previous findings on simple models. 32, a paper, found that two-layer neural networks in early stages of training tend to learn a linear approximation to a problem. Although the technicalities of our data generation process do not precisely match the hypotheses of their theorem, it seems likely that the same basic mechanism is at work. In our case, we see the toy network learns a linear PCA solution before moving to a better nonlinear solution. A second related finding comes from 33, who looked at hierarchical sets of features with a data generation process similar to the one we consider. They find empirically that certain networks, nonlinear and deep linear, split embedding vectors in a manner very much like what we observed. They also provide a theoretical analysis in terms of the underlying dynamical system. A key difference is that they focus on the topology, the branching structure of the emerging feature representations, rather than the geometry. Despite this difference, it seems likely that their analysis could be generalized to our case. Relationship to adversarial robustness. Although we're most interested in the implications of superposition for interpretability, there appears to be a connection to adversarial examples. If one gives it a little thought, this connection can actually be quite intuitive. In a model without superposition, the end-to-end weights for the first feature are WTW naught equals 1, 0, 0, 0, 0, and so on. But in a model with superposition, it's something like WTW naught equals 1, epsilon, negative epsilon, epsilon, so on. The epsilon entries, which are solely an artifact of superposition interference, create an obvious way for an adversary to attack the most important feature. Note that this may remain true even in the infinite data limit. The optimal behavior of the model fit to sparse infinite data is to use superposition to represent more features, leaving it vulnerable to attack. To test this, we generated L2 adversarial examples, allowing a max L2 attack norm of 0.1 of the average input norm. We originally generated attacks with gradient descent, but found that for extremely sparse examples where ReLU neurons are in the zero regime 99% of the time, attacks were difficult, effectively due to gradient masking. Instead, we found it worked better to analytically derive adversarial attacks by considering the optimal L2 attacks for each feature, lambda times WTWI over the norm of WTWI 2. And taking the one of these attacks which most harms model performance. We find the vulnerability to adversarial examples sharply increases as superposition forms, increasing by greater than 3x, and that the level of vulnerability closely tracks the number of features per dimension, the reciprocal of feature dimensionality. Here we see some graphs, vulnerability to adversarial examples relative to non-superposition model, L prime minus L over L prime naught minus L naught. The model's vulnerability to adversarial examples increases with feature sparsity, tracking the features per dimension measure of superposition plotted below. We see models start to use superposition and it starts to go up, plateaus for a bit, then models use more than antipodal superposition and it goes up. Below that we have features per dimension, 1 over d star equals the Frobenius norm squared of w over m. Here we plot the number of features per dimension, the reciprocal of the dimensionality we defined in the previous section. We see that the curve closely parallels vulnerability to adversarial examples. And you see these two lines from above as well. Starts to go up a little bit, models start to use superposition, plateaus for a bit, and then goes up again as models use more than antipodal superposition. And this is on the x-axis from dense to sparse. We can also directly plot adversarial vulnerability against the number of features per dimension. This reveals that adversarial vulnerability is highly correlated with the number of features stored in superposition per dimension. Here we see this smaller graph. X is features per dimension, which is going from 1 to 5, and adversarial vulnerabilities going from 1x to 8x, and it's increasing. We're hesitant to speculate about the extent to which superposition is responsible for adversarial examples in practice. There are compelling theories for why adversarial examples occur without reference to superposition, but it is interesting to note that if one wanted to try to argue for a superposition maximalist stance, it does seem like many interesting phenomena related to adversarial examples can be predicted from superposition. As seen above, superposition can be used to explain why adversarial examples exist. It also predicts that adversarially robust models would have worse performance, since making models robust would require giving up superposition and representing less features. It predicts that more adversarially robust models might be more interpretable. Finally, it could arguably predict that adversarial examples transfer if the arrangement of features in superposition is heavily influenced by which features are correlated or anti-correlated. It might be interesting for future work to see how far the hypothesis that superposition is a significant contributor to adversarial examples can be driven. In addition to observing that superposition can cause models to be vulnerable to adversarial examples, we briefly experimented with adversarial training to see if the relationship could be used in the other direction to reduce superposition. To keep training reasonably efficient, we used the analytic optimal attack against a random feature. We found that this did reduce superposition, but attacks had to be made unreasonably large, 80% input L2 norm, to fully eliminate it, which didn't seem satisfying. Perhaps stronger adversarial attacks would work better. We didn't explore this further since the increased cost and complexity of adversarial training made us want to prioritize other lines of attack on superposition first. Superposition in a privileged basis. So far, we've explored superposition in a model without a privileged basis. We can rotate the hidden activations arbitrarily, and as long as we rotate all the weights, we have the exact same model behavior. That is, for any ReLU output model with weights W, we could take an arbitrary orthogonal matrix O and consider the model W prime equals OW, since OW transpose OW equals W transpose W. The result would be an identical model. Models without a privileged basis are elegant, and can be an interesting analog for certain neural network representations which don't have a privileged basis, word embeddings, or the transformer residual stream. But we'd also, and perhaps primarily, like to understand neural network representations where there are neurons which do impose a privileged basis, such as a transformer MLP layers or convnet neurons. Our goal in this section is to explore the simplest toy model which gives us a privileged basis. There are at least two ways we could do this. We could add an activation function or apply L1 regularization to the hidden layer. We'll focus on adding an activation function, since the representation we are most interested in understanding is hidden layers with neurons, such as the transformer MLP layer. This gives us the following ReLU hidden layer model. H equals ReLU of WX, X prime equals ReLU of WT, H plus B. We'll train this model on the same data as before. Adding a ReLU to the hidden layer radically changes the model from an interpretability perspective. The key thing is that while W in our previous model was challenging to interpret, recall that we visualized WTW rather than W in the ReLU hidden layer model can be directly interpreted since it connects features to basis-aligned neurons. We'll discuss this in much more detail shortly, but here's a comparison of weight results from a linear hidden layer model and a ReLU hidden layer model. Here we have a diagram of privileged basis makes W directly interpretable. No superposition. W hidden layer, W ReLU layer. So the W hidden layer it looks like noise, whereas the W ReLU hidden is on the diagonal. 6 features in 5 dimensions. W linear hidden, again, looks like noise. W ReLU hidden looks like 3 on the diagonal, and then it sort of breaks down into not exactly noise, but a lot of negative ones and ones, but more ones than negative ones, or at least more high values than low values, but still very, polarized. And then next to this we have 8 features in 5 dimensions. W linear hidden, again, looks like noise. W ReLU hidden has some, you know, sort of complementary structures, but still looks very organized. Recall that we think of basis elements in the input as features, and basis elements in the middle layer as neurons. Thus, W is a map from features to neurons. What we see in the above plot is that the features are aligning with neurons in a structured way. Many of the neurons are simply dedicated to representing a feature. This is the critical property that justifies why neuron-focused interpretability approaches, such as much of the work in the original circuits thread, can be effective in some circumstances. Let's explore this in more detail. Visualizing superposition in terms of neurons. Having a privileged basis opens up new possibilities for visualizing our models. As we saw above, we can simply inspect W. We can also make a per neuron stacked bar plot where, for every neuron, we visualize its weights as a stack of rectangles on top of each other. Each column in the stack plot visualizes one column of W. Each rectangle represents one weight entry, with height corresponding to the absolute value. The color of each rectangle corresponds to the feature it acts on, i.e., which row of W it's in. Negative values go below the x-axis. The order of the rectangles is not significant. This stack plot visualization can be nice as models get bigger. It also makes polysemantic neurons obvious. They simply correspond to having more than one weight. W is matrix. Since the hidden layer now has a privileged basis, can visualize the raw weight matrix. So we see neurons, features. Let's assign a color to each feature for the stack plot. Okay, I see. So the top feature becomes green, the middle feature becomes yellow, and the bottom feature becomes orange. Then W as stack plot. Instead of showing a matrix, we can map features to colors and stack the weights per neuron. Each column corresponds to a neuron. A neuron with multiple features is polysemantic. Okay, interesting. So let's think about this. We're not showing a matrix now. We're mapping features to colors and stacking the weights per neuron. So if I go for the first neuron, it only has the one orange feature. If I look at the second neuron, it has the one yellow feature and the one green feature. And then if I look at the third neuron, it has blue and red and gray on the weight matrix. But when I look at the stack plot, that second feature is above as yellow and the third feature is below as blue. And again, a neuron with multiple features is polysemantic. Each column corresponds to a neuron. And also, again, this is meant to make polysemantic neurons obvious. They simply correspond to having more than one weight. Okay. And again, the negative values go below x-axis. Okay. We'll now visualize a ReLU hidden layer toy model with n equals 10, m equals 5, importance I equals 0.75 to the I, and varying feature sparsity levels. We choose a very small model, only 5 neurons, both for ease of visualization and to circumvent some issues with this toy model we'll discuss below. However, we found that these small models were harder to optimize. For each model shown, we trained 1,000 models and visualized the one with the lowest loss. Although the typical solutions are often similar to the minimal loss solutions shown, selecting the minimal loss solutions reveals even more structure in how features align with neurons. It also reveals that there are ranges of sparsity values where the optimal solution for all models trained on data with that sparsity have the same weight configurations. The solutions are visualized below, both visualizing the raw W in a neuron stacked bar plot. We color features in the stacked bar plot based on whether they're in superposition, and color neurons as being monosemantic or polysemantic, depending on whether they store more than one feature. Neuron order was chosen by hand since it's arbitrary. And we see all monosemantic neurons approximately 0.5 less than or equal to 1 minus s. In this regime, every feature gets a dedicated neuron. That is, the model consists entirely of monosemantic neurons. So W neurons, features, neuron weight, stacked bar plot, monosemantic neurons. As feature sparsity increases, we see neurons shift from being monosemantic, purple, to being polysemantic. Below, we see 3 features and 2 neurons, approximately 0.2 less than or equal to 1 minus s. So 1 minus s is between 0.2 and 0.5. In this regime, the 3 most important features still get dedicated neurons, but the next three are represented in a kind of binary code by two neurons' activations. These two neurons form a binary code for three features. Note that the 1-1 feature is orthogonal to the others, while the other two are an antipodal pair. 5 features and 3 neurons. At this sparsity level, which seems quite narrow, just 1 minus s equals 0.15, we still see 2 monosemantic neurons and 3 polysemantic neurons. The 3 polysemantic neurons implement a code that doesn't have any very simple explanation. 6 features and 4 neurons, 1 minus s equals 0.12. In this regime, we have 1 monosemantic neuron. The 4 polysemantic neurons implement an interesting code. One neuron seems to distinguish between important and unimportant features. The important features are then encoded as sets of 2 of the other 3 neurons, while unimportant features are represented by 1 neuron. 8 features and 5 neurons. 1 minus s is between 0.05 and 0.08. In this regime, all neurons are polysemantic. The code is a kind of extension of the one described previously. One distinguishes important and unimportant features. Then either sets of 3 of the other neurons or a single other neuron are used to distinguish the specific feature. Features as pairs of neurons, 1 minus s less than or equal to 0.04. In this regime, each feature simply corresponds to a pair of neurons. Presumably, if there were more features, increasing sparsity would eventually produce a dense binary code, but with only 10 features, this is the densest code that forms. The most important thing to pay attention to is how there's a shift from monosemantic to polysemantic neurons as sparsity increases. Monosemantic neurons do exist in some regimes. Polysemantic neurons exist in others, and they can both exist in the same model. Moreover, while it's not quite clear how to formalize this, it looks a great deal like there's a neuron-level phase change, mirroring the feature phase changes we saw earlier. It's also interesting to examine the structure of the polysemantic solutions, which turn out to be surprisingly structured and neuron-aligned. Features typically correspond to sets of neurons. Monosemantic neurons might be seen as the special case where features only correspond to singleton sets. There's also structure in how polysemantic neurons are. They transition from monosemantic to only representing a few features to gradually representing more. However, it's unclear how much of this is generalizable to real models. Limitations of the ReLU hidden layer toy model simulating identity. Unfortunately, the toy model described in this section has a significant weakness, which limits the regimes in which Unfortunately, the toy model described in this section has a significant weakness, which limits the regimes in which it shows interesting results. The issue is that the model doesn't benefit from the ReLU hidden layer. It has no role except limiting how the model can encode information. If given any chance, the model will circumvent it. For example, given a hidden layer bias, the model will set all the biases to be positive, shifting the neurons into a positive regime where they behave linearly. If one removes the bias, but gives the model enough features, it will simulate a bias by averaging over many features. The model will only use the ReLU activation function if absolutely forced, which is a significant mark against studying this toy model. We'll introduce a model without this issue in the next section, but wanted to study this model as a simpler case study. Computation and superposition. So far, we've shown that neural networks can store sparse features in superposition and then recover them. But we actually believe superposition is more powerful than this. We think that neural networks can perform computation entirely in superposition, rather than just using it as storage. This model will also give us a more principled way to study a privileged basis, where features align with basis dimensions. To explore this, we consider a new setup where we imagine our input and output layer to be the layers of our hypothetical disentangled model, but have our hidden layer be a smaller layer we're imagining to be the observed model, which might use superposition. We'll then try to compute a simple nonlinear function and explore whether it can use superposition to do this. Since the model will have and need to use the hidden layer nonlinearity, we'll also see features align with a privileged basis, hypothetical disentangled model. Below that, the observed model, and they connect. Can neural networks do useful computation in superposition, in addition to just representing features? We replace a single layer of an imagined larger network with a lower dimensional model and study what happens. Specifically, we'll have the model compute y equals absolute value of x. Absolute value is an appealing function to study because there's a very simple way to compute it with ReLU neurons. Absolute of x equals ReLU of x plus ReLU of negative x. This simple structure will make it easy for us to study the geometry of how the hidden layer is leveraged to do computation. Since this model needs ReLU to compute absolute value, it doesn't have the issues the model in the previous section had with trying to avoid the activation function. Experiment setup. The input feature vector x is still sparse, with each feature x sub I having probability s sub I of being 0. However, since we want to have the model compute absolute value, we need to allow it to take on non-positive values for this to be a non-trivial task. As a result, if it is non-zero, its value is now sampled uniformly from -1 to 1. The target output y is y equals absolute of x. Following the previous section, we'll consider the ReLU hidden layer toy model variant, but no longer tie the two weights to be identical. H equals ReLU of weight 1 times x, h prime equals ReLU of weight 2 times h plus b. The loss is still the mean squared error weighted by feature importances I, as before. Basic results. With this model, it's a bit less straightforward to study how individual features get embedded. Because of the ReLU on the hidden layer, we can't just study weight 2 transpose weight 1. And because weight 2 and weight 1 are now learned independently, we can't just study columns of weight 1. We believe that with some manipulation, we could recover much of the simplicity of the earlier model by considering positive features and negative features independently, but we're going to focus on another perspective instead. As we saw in the previous section, having a hidden layer activation function means that it makes sense to visualize the weights in terms of neurons. We can visualize W directly, or as a neuron stack plot as we did before. We can also visualize it as a graph, which can sometimes be helpful for understanding computation. So W as matrix, since the hidden layer now has a privileged basis, can visualize the raw weight matrix. So features and neurons. First feature has one neuron, I'll call it the left neuron. Then the next feature has the right neuron, and the third feature has weakly the right neuron. W as stack plot. Instead of showing a matrix, we can map features to colors and stack the weights per neuron. So the first neuron has just the orange from the first feature, and the second neuron, I'll call it like a light orange from the second feature, and then the dark green from the third feature. Maybe better to call it a almost dark green, since it's not meant to represent a fully activated neuron, right? And then W as graph. We can also visualize weights as the edges of a graph, as is often done for neural nets. Then you see neuron maps to this one, this orange is mapping to this one, and then for the second one, the lighter orange maps to it, but also weakly the green maps to it. Okay, let's look at what happens when we train a model with n equals 3 features to perform absolute value on m equals 6 hidden layer neurons. Without superposition, the model needs 2 hidden layer neurons to implement absolute value on one feature. The resulting model, modulo a subtle issue about rescaling input and output weights, performs absolute value exactly as one might expect. For each input feature x sub I, it constructs a positive side neuron ReLU of x sub I and a negative side neuron ReLU of negative x sub I. It then adds these together to compute absolute value. Raw weights visualization, weights 1 input to neuron weights, and then weights 2 input to neuron weights, and we see this sort of crossing back and forth on weight 1, whereas they all stay above on weight 2 at different shades, representing, I believe, the different features. And in the graph visualization, we see orange is going to this first node and the second node on the +1 and the -1 respectively, and then these are mapping to this orange in weight 2. Likewise, light orange is mapping to 2 nodes, +1, -1 respectively, and then these are mapping to 1 orange in weight 2, and repeated for the green. Superposition versus sparsity. We've seen that, as expected, our toy model can learn to implement absolute value, but can it use superposition to compute absolute value for more features? To test this, we train models with n equals 100 features and m equals 40 neurons, and a feature importance curve, importance equals 0.8 to the I, varying feature sparsity. A couple of notes on visualization. Since we're primarily interested in understanding superposition and polysemantic neurons, we'll show a stacked weight plot of the absolute values of weights. The features are colored by superposition. To make the diagrams easier to read, neurons are faintly colored based on how polysemantic they are, as judged by I based on the plots. Neuron order is sorted by the importance of the largest feature. ReLU hidden layer toy model on absolute value task, n equals 100, m equals 40, I equals 0.8 to the I. Neurons sorted by importance of largest feature. So in the dense regime, all neurons are monosemantic, dedicated to a single feature. Continue to move down, and neurons start to become, so I'll just read. So originally dense, then neurons continue to be monosemantic to moderate sparsity levels. Eventually we start to see a few slightly polysemantic neurons. As sparsity increases further, we see a small number of highly polysemantic neurons representing low importance features. The number of polysemantic neurons grows by the time we're at 1 minus s equals 0.01, and they become even more polysemantic. Eventually, all neurons are highly polysemantic, and this is when we reach 1 minus s equals 0.001. Much like we saw in the ReLU hidden layer models, these results demonstrate that activation functions under the right circumstances create a privileged basis and cause features to align with basic dimensions. In the dense regime, we end up with each neuron representing a single feature, and we can read feature values directly off of neuron activations. However, once the features become sufficiently sparse, this model too uses superposition to represent more features than it has neurons. This result is notable because it demonstrates the ability of neural networks to perform computation even on data that is represented in superposition. Remember that the model is required to use the hidden layer ReLU in order to compute an absolute value. Gradient descent manages to find solutions that usefully approximate the computation even when each neuron encodes a mix of multiple features. Focusing on the intermediate sparsity regimes, we find several additional qualitative behaviors that we find fascinatingly reminiscent of behavior that has been observed in real full-scale neural networks. So here we see a diagram, neurons sorted by importance of largest features, 1 minus s equals 0.01. Neurons can be monosemantic and polysemantic in the same model. And it's about, let's call it half and half. To begin, we find, to note though, those which are polysemantic are mostly lowly polysemantic, whereas those which are monosemantic, of course, are monosemantic. And there are some sort of which overlap, which have very, very, very slight polysemanticity. To begin, we find that in some regimes, many of the model's neurons will encode pure features, but a subset of them will be highly polysemantic. This is similar to the phase change we saw earlier in the ReLU output model. However, in that case, the phase change was with respect to features with more important features not being put in superposition. In this experiment, the neurons don't have any intrinsic importance, but we see that the neurons representing the most important features on the left tend to be monosemantic. We find this to bear a suggestive resemblance to some previous work in vision models, which found some layers that contained mostly pure feature neurons, but with some neurons representing additional features on a different scale. We also note that many neurons appear to be associated with a single primary feature, encoded by a relatively large weight, coupled with one or more secondary features, encoded with smaller magnitude weights to that neuron. If we were to observe the activations of such a neuron over a range of input examples, we would find that the largest activations of that neuron were all or nearly associated with the presence of the primary feature, but that the lower magnitude activations were much more polysemantic. Intriguingly, that description closely matches what researchers have found in previous work on language models. Many neurons appear interpretable when we examine their strongest activations over a dataset, but can be shown on further investigation to activate for other meanings or patterns, often at a lower magnitude. While only suggestive, the ability of our toy model to reproduce these qualitative features of larger neural networks offers an exciting hint that these models are illuminating general phenomena. The asymmetric superposition motif. If neural networks can perform computation in superposition, a natural question to ask is how exactly they're doing so. What does that look like mechanically in terms of the weights? In this subsection, we will mostly work through one such model and see an interesting motif of asymmetric superposition. We use the term motif in the sense of the original circuit thread inspired by its use in systems biology. The model we're trying to understand is shown below on the left, visualized as a neuron weight stack plot with features corresponding to colors. The model is only doing a limited amount of superposition, and many of the weights can be understood as simply implementing absolute value in the expected way. However, there are a few neurons doing something else. At first glance, this model is quite complicated and tricky to understand. However, we can mostly decompose it into two pieces. So you see the input weights, then the output weights. Each column shows one neuron. Many weights are simply implementing absolute value, or a single side of absolute value in the expected way. The main other thing is asymmetric superposition with inhibition. The model has two instances of this motif. These other neurons implement two instances of asymmetric superposition and inhibition. Each instance consists of two neurons. Asymmetric superposition with inhibition instance 1. Asymmetric superposition, you see the input and the output sizes are flipped, and the inhibition input and output one is clearly greater than the other. Asymmetric superposition with inhibition instance 2. Asymmetric superposition, input output sizes flipped, inhibition input output one is greater than the other. One neuron does asymmetric superposition. In normal superposition, one might store features with equal weights, e.g. W equals 1, negative 1, and then have equal output weights, W equals 1, 1. In asymmetric superposition, one stores the features with different magnitudes, e.g. W equals 2, negative 1 over 2, and then has reciprocal output weights, e.g. W equals 1 half, 2. This causes one feature to heavily interfere with the other, but avoid the other interfering with the first. To avoid the consequences of that interference, the model has another neuron heavily inhibit the feature in the case where there would have been positive interference. This essentially converts positive interference, which could greatly increase the loss, into negative interference, which has limited consequences due to the output ReLU. One neuron represents two features, tan and red, with asymmetric superposition. This causes tan to heavily interfere with red, but not the reverse. Large amounts of positive interference are bad, so the model then puts a small amount of tan into the neuron and uses it to massively inhibit red. This also forces the main feature the neuron is operating on, blue, to inhibit red. And just thinking this out loud, we see that on the left side, the one with a slight positive red and a big negative tan is multiplied by the one with just the positive red, a big positive red stacked under the positive tan. The small red times the big red equals 1, and the big negative tan times the big negative red is greater than 1. And the small negative red times the small positive tan. The small positive red times the small positive tan has an absolute value less than 1. And that's not absolute value, I think that's matrix small. Regardless, the big negative tan times the small positive tan equals 1. Okay. And that's for asymmetric superposition. On the right, we have a medium-sized negative blue times the positive medium blue equals 1. The medium negative blue times the big negative red is greater than 1. The very slight tan times the medium blue is less than 1, and the very slight negative tan times the very large negative red is greater than 1. There are a few other weights this doesn't explain. We believe they're effectively small conditional biases, but this asymmetric superposition and inhibition pattern appears to be the primary story. The strategic picture of superposition. Although superposition is scientifically interesting, much of our interest comes from a pragmatic motivation. We believe that superposition is deeply connected to the challenge of using interpretability to make claims about the safety of AI systems. In particular, it is a clear challenge to the most promising path we see to be able to say that neural networks won't perform certain harmful behaviors or to catch unknown unknowns, safety problems. This is because superposition is deeply linked to the ability to identify and enumerate over all features in a model, and the ability to enumerate over all features would be a powerful primitive for making claims about model behavior. We begin this section by describing how solving superposition, in a certain sense, is equivalent to many strong interpretability properties which might be useful for safety. Next, we'll describe 3 high-level strategies one might take to solving superposition. Finally, we'll describe a few other additional strategic concerns: safety, interpretability, and solving superposition. We'd like a way to have confidence that models will never do certain behaviors, such as deliberately deceive or manipulate. Today, it's unclear how one might show this, but we believe a promising tool would be the ability to identify and enumerate over all features. The ability to have a universal quantifier over the fundamental units of neural network computation is a significant step towards saying that certain types of circuits don't exist. It also seems like a powerful tool for addressing unknown unknowns, since it's a way that one can fully cover network behavior in a sense. How does this relate to superposition? It turns out that the ability to enumerate over features is deeply intertwined with superposition. One way to see this is to imagine a neural network with a privileged basis and without superposition, like the monosemantic neurons found in early Inception v1. Features would simply correspond to neurons, and you could enumerate over features by enumerating over neurons. The connection also goes the other way. If one has the ability to enumerate over features, one can perform compressed sensing using the feature directions to, with high probability, unfold a superposition model's activations into those of a larger non-superposition model. I'm going to read that part again. The connection also goes the other way. If one has the ability to enumerate over all features, one can perform compressed sensing using the feature directions to, with high probability, unfold a superposition model's activations into those of a larger non-superposition model. For this reason, we'll call any method that gives us the ability to enumerate over features and equivalently unfold activations a solution to superposition. Again, we'll call any method that gives us the ability to enumerate over features and equivalently unfold activations a solution to superposition. Any solution is on the table, from creating models that just don't have superposition to identifying what directions correspond to features after the fact. We'll discuss the space of possibilities shortly. We've motivated solving superposition in terms of feature enumeration, but it's worth noting that it's equivalent to, or necessary for, many other interpretability properties one might care about. Decomposing activation space. The most fundamental challenge of any interpretability agenda is to defeat the curse of dimensionality. For mechanistic interpretability, this ultimately reduces to whether we can decompose activation space into independently understandable components, analogous to how computer program memory can be decomposed into variables. Identifying features is what allows us to decompose the model in terms of them. Describing activations in terms of pure features. One of the most obvious casualties of superposition is that we can't describe activations in terms of pure features. When features are relatively basis aligned, we can take an activation, say the activations for a dog head in a vision model, and decompose them into individual underlying features like a floppy ear, short golden fur, and a snout. See the semantic dictionary interface and building blocks. Solving superposition would allow us to do this for every model. Understanding weights, i.e., circuit analysis. Neural network weights can typically only be understood when they're connecting together understandable features. All the circuit analysis seen in the original circuit thread, especially this one paper, was fundamentally only possible because the weights connected non-polysemantic neurons. We need to solve superposition for this to work in general. Even very basic approaches become perilous with superposition. It isn't just sophisticated approaches to interpretability which are harmed by superposition. Even very basic methods one might consider become unreliable. For example, if one is concerned about language models exhibiting manipulative behavior, one might ask if an input has a significant cosine similarity to the representations of other examples of deceptive behavior. Unfortunately, superposition means that cosine similarity has the potential to be misleading, since unrelated features start to be embedded with positive dot products to each other. However, if we solve superposition, this won't be an issue. Either we'll have a model where features align with neurons, or a way to use compressed sensing to lift features to a space where they no longer have positive dot products. 3 ways out. At a very high level, there seem to be 3 potential approaches to resolving superposition. Create models without superposition. Find an overcomplete basis that describes how features are represented in models with superposition. Hybrid approaches, in which one changes models, not resolving superposition, but making it easier for a second stage of analysis to find an overcomplete basis that describes it. Our sense is that all of these approaches are possible if one doesn't care about having a competitive model. For example, we believe it's possible to accomplish any of these for the toy models described in this paper. However, as one starts to consider serious neural networks, let alone modern large language models, all of these approaches begin to look very difficult. We'll outline the challenges we see for each approach in the following sections. With that said, it's worth highlighting one bright spot before we focus on the challenges. You might have believed that superposition was something you could never fully get rid of, but that doesn't seem to be the case. All our results seem to suggest that superposition and polysemanticity are phases with sharp transitions. That is, there may exist a regime for every model where it has no superposition or polysemanticity. The question is largely whether the cost of getting rid of or otherwise resolving superposition is too high. Approach 1. Creating models without superposition. It's actually quite easy to get rid of superposition in the toy models described in this paper, albeit at the cost of a higher loss. Simply apply at L1 regularization term to the hidden layer activations, i.e. add lambda times h norm 1 to the loss. This actually has a nice interpretation in terms of killing features below a certain importance threshold, especially if they're not basis aligned. Generalizing this to real neural networks isn't trivial, but we expect it can be done. This approach would be similar to work attempting to use sparsity to encourage basis-aligned word embeddings. However, it seems likely that models are significantly benefiting from superposition. Roughly, the sparser features are, the more features can be squeezed in per neuron, and many features in language models seem very sparse. For example, language models know about individuals with only modest public presences, such as several of the authors of this paper. Presumably, we only occur with frequencies significantly less than 1 in a million tokens. As a result, it may be the case that superposition effectively makes models much bigger. All of this paints a picture where getting rid of superposition may be fairly achievable, but doing so will have a large performance cost. For a model with a fixed number of neurons, superposition helps potentially a lot. But this is only true if the constraint is thought of in terms of neurons. That is, a superposition model with n neurons likely has the same performance as a significantly larger monosemantic model with kn neurons. But neurons aren't the fundamental constraint. Flops are. In the most common model architectures, flops and neurons have a strict correspondence, but this doesn't have to be the case, and it's much less clear that superposition is optimal in the broader space of possibilities. One family of models which change the flop to neuron relationship are mixture of expert models, MOE models. The intuition is that most neurons are for specialized circumstances and don't need to activate most of the time. For example, German-specific neurons don't need to activate on French text. Harry Potter neurons don't need to activate on scientific papers. So mixture of expert models organize neurons into blocks or experts, which only activate a small fraction of the time. This effectively allows the model to have k times more neurons for a similar flop budget, given the constraint that only 1 over k of the neurons activate in a given example, and that they must activate in a block. Put another way, mixture of expert models can recover neuron sparsity as free flops, as long as the sparsity is organized in certain ways. It's unclear how far this can be pushed, especially given difficult engineering constraints, but there's an obvious lower bound, which is likely too optimistic, but is interesting to think about. What if models only expended flops on neuron activations and recovered the compute of all non-activating neurons? In this world, it seems unlikely that superposition would be optimal. You could always split a polysemantic neuron into dedicated neurons for each feature with the same cost, except for the cases where there would have been interference that hurt the model anyways. Our preliminary investigations comparing various types of superposition in terms of loss reduction per activation frequency seem to suggest that superposition is not optimal on these terms, although it asymptotically becomes as good as dedicated feature dimensions. Another way to think of this is that superposition exploits a gap between the sparsity of neurons and the sparsity of the underlying features. Mixture of experts eats at that same gap, and so we should expect a mixture of expert models to have less superposition. To be clear, MOE models are already well studied, and we don't think this changes the capabilities case for them. If anything, superposition offers a theory of why MOE models have not proven more effective for capabilities when the case for them seems so initially compelling. But if one's goal is to create competitive models that don't have superposition, MOE models become interesting to think about. We don't necessarily think that they significantly are, or that they specifically are the right path forward. Our goal here has been to use them as an example of why we think it remains plausible there may be ways to build competitive superposition-free models. Approach 2. Finding an overcomplete basis. The opposite strategy of creating a superposition-free model is to take a regular model, which has superposition, and find an overcomplete basis describing how features are embedded after the fact. This appears to be a relatively standard sparse coding or dictionary learning problem, where we want to take the activations of neural network layers and find out which directions correspond to features. This approach has been explored by some prior work. The advantage of this is that we don't need to worry about whether we're damaging model performance. On the other hand, many other things are harder. It's no longer easy to know how many features you have to enumerate. A monosemantic model represents a feature per neuron, but when finding an overcomplete basis, there's an additional challenge of identifying how many features to use it for. Solutions are no longer integrated into the surface computational structure. Neural networks can be understood in terms of their surface structure, neurons, attention heads, etc., and virtual structure that implicitly emerge, e.g. virtual attention heads. A model described by an overcomplete basis has virtual neurons. There's a further gap between the surface and virtual structure. It's a difficult major engineering challenge. Seriously attempting to solve superposition by applying sparse coding to real neural nets suggests a massive sparse coding problem. For truly large language models, one would be starting with something like a millions neurons by billions tokens matrix, and then trying to do an extremely over-complete factorization, perhaps trying to factor it to be 1,000 or more times larger. This is a major engineering challenge, which is different from the standard distributed training challenges ML labs are set up for. Interference is no longer pushing in your favor. If you try to train models without superposition, interference between features is pushing the training process to have less superposition. If you instead try to decode superposition after the fact, and you don't have part of the objective pushing in your favor. Approach 3. Hybrid approaches. In addition to approaches which address superposition purely at training time or purely after the fact, it may be possible to take hybrid approaches which do a mixture. For example, even if one can't change models without superposition, it may be possible to produce models with less superposition, which are then easier to decode. Alternatively, it may be possible for architecture changes to make finding an overcomplete basis easier or more computationally tractable in large models, separately from trying to reduce superposition. Additional constraints. Phase changes as cause for hope. Is totally getting rid of superposition a realistic hope? One could easily imagine a world where it can only be asymptotically reduced and never fully eliminated. While the results in this paper seem to suggest that superposition is hard to get rid of because it's actually very useful, the upshot of it corresponding to a phase change is that there's a regime where it totally doesn't exist. If we can find a way to push models in the non-superposition regime, it seems likely it can be totally eliminated. Any superposition-free model would be a powerful tool for research. We believe that most of the research risk is in whether one can make performant superposition-free models, rather than whether it's possible to make superposition-free models at all. Of course, ultimately, we need to make performant models, but a non-performant superposition-free model could still be a very useful research tool for studying superposition in normal models. At present, it's challenging to study superposition in models because we have no ground truth for what the features are. This is also the reason why the toy models described in this paper can be studied. We do know what the features are. If we had a superposition-free model, we may be able to use it as a ground truth to study superposition in regular models. Local bases are not enough. Earlier, when we considered the geometry of non-uniform superposition, we observed that models often form local orthogonal bases, where co-occurring features are orthogonal. This suggests a strategy for locally understanding models on sufficiently narrow subdistributions. However, if our goal is to eventually make useful statements about the safety of models, we need mechanistic accounts that hold for the full distribution and off distribution. Local bases seem unlikely to give this to us. Discussion. To what extent does superposition exist in real models? Why are we interested in toy models? We believe they are useful proxies for studying the superposition we suspect might exist in real neural networks. But how can we know if they're actually a useful toy model? Our best validation is whether their predictions are consistent with empirical observations regarding polysemanticity. To the best of our knowledge, they are. In particular, polysemantic neurons exist. Polysemantic neurons form in our third model, just as they are observed in a wide range of neural networks. Neurons are sometimes cleanly interpretable and sometimes polysemantic, often in the same layer. Our third model exhibits both polysemantic and non-polysemantic neurons, often at the same time. This is analogous to how real neural networks often have a mixture of polysemantic and non-polysemantic neurons in the same layer. Inception V1 has more polysemantic neurons in later layers. Empirically, the fraction of neurons which are polysemantic in Inception V1 increases with depth. One natural explanation is that as features become higher level, the stimuli they detect become rarer and thus sparser. For example, in vision, a high-level floppy ear feature is less common than a low-level Gabor filter's edge. A major prediction of our model is that superposition and polysemanticity increase as sparsity increases. Early transformer MLP neurons are extremely polysemantic. Our experience is that neurons in the first MLP layer in transformer language models are often extremely polysemantic. If the goal of the first MLP layer is to distinguish between different interpretations of the same token, e.g. die in English versus German versus Dutch versus Afrikaans, such features would be very sparse and our toy model would predict lots of polysemanticity. This doesn't mean that everything about our toy model reflects real neural networks. Our intuition is that some of the phenomena we observe, superposition, monosemantic versus polysemantic neurons, perhaps the relationship to adversarial examples, are likely to generalize, while other phenomena, especially the geometry and learning dynamics results, are much more uncertain. Open questions. This paper has shown that the superposition hypothesis is true in certain toy models, but if anything, we're left with many more questions about it than we had at the start. In this final section, we review some of the questions which strike us as important. What do we know? And would we like for future work to clarify? Is there a statistical test for catching superposition? How can we control whether superposition and polysemanticity occur? Put another way, can we change the phase diagram such that features don't fall into the superposition regime? Pragmatically, this seems like the most important question. L1 regularization of activations, adversarial training, and changing the activation function all seem promising. Are there any models of superposition which have a closed-form solution? Sachs et al. Demonstrate that it's possible to create nice closed-form solutions for linear neural networks. We made some progress toward this for the n equals 2, m equals 1 ReLU output model, and Tom McGrath makes further progress in his comment, but it would be nice to solve this more generally. How realistic are these toy models? To what extent do they capture the important properties of real models with respect to superposition? How can we tell? Can we estimate the feature importance curve or feature sparsity curve of real models? If one takes our toy model seriously, the most important properties for understanding the problem are the feature importance and sparsity curves. Is there a way we can estimate them for real models? Likely, this would involve training models of varying sizes or amounts of regularization, observing the loss in neuron sparsities, and trying to infer something. Should we expect superposition to go away if we just scale enough? What assumptions about the feature importance curve and sparsity would need to be true for that to be the case? Alternatively, should we expect superposition to remain a constant fraction of represented features, or even to increase as we scale? Are we measuring the maximally principled things? For example, what is the most principled definition of superposition/polysemanticity? How important are polysemantic neurons? If X% of the model is interpretable neurons and 1 minus X% are polysemantic, how much should we believe we understand from understanding the X% interpretable neurons? See also the feature packing principle suggested above. How many features should we expect to be stored in superposition? This was briefly discussed in the previous section. It seems like results from compressed sensing should be able to give us useful upper bounds, but it would be nice to have a clearer understanding, and perhaps tighter bounds. Does the apparent phase change we observe in features/neurons have any connection to phase changes in compressed sensing? How does superposition relate to non-robust features? An interesting paper by Gabriel Go, archive.org backup, explores features in a linear model in terms of the principal components of the data. It focuses on a trade-off between usefulness and robustness in the principal component features, but it seems like one could also relate it to the interpretability of features. How much would this perspective change if one believed the superposition hypothesis? Could it be that the useful, non-robust features are an artifact of superposition? To what extent can neural networks do useful computation on features in superposition? Is the absolute value problem representative of computation in superposition generally, or idiosyncratic? What class of computation is amenable to being performed in superposition? Does it require a sparse structure to the computation? How does superposition change if features are not independent? Can superposition pack features more efficiently if they are anti-correlated? Can models effectively use nonlinear representations? We suspect models will tend not to use them, but further experimentation could provide good evidence. See the appendix on nonlinear compression. For example, investigating the representations used by autoencoders with multi-layer encoders and decoders with really small bottlenecks on random and correlated data. And at the bottom here, they have a bunch of related work, which I'm sure is all very interesting. But we made it to the real end, and so I'm going to take off. And yeah, that was a really interesting paper, though. Really super duper interesting. Definitely gotta reread it. And this whole notion of polysemanticity is beautiful when viewed geometrically. I don't know how much I can really extend the idea of geometry to these real models like they say, but at least if you just roll with it and you just picture these lines that are almost orthogonal, operating in this ridiculously high dimensional space, and our ability to capture information from them even though there's interference, and then represent just, way more concepts than you have neurons. It's just insane. It really makes me wish you could create like real, 1,000-dimensional visualizations and just see what it looks like to be inside a transformer. I know it's not possible, but just it's so mind bending, right? But it's beautiful geometrically. But yeah, peace out.